What is Kafka and what problem does it solve? What is Kafka? Apache Kafka is a distributed event streaming platform. At its core, Kafka is a commit log where services write data and other services read that data from. Kafka was originally developed at LinkedIn in 2011 to solve large-scale activity tracking problems. Later it was open-sourced and is now maintained by the Apache Software Foundation. Kafka can be understood in three main roles. 1. Kafka is a message broker. This means different services send messages to Kafka and other services receive those messages from Kafka. 2. Kafka is an event store. This means every message written into Kafka is stored on disk and is not deleted immediately after it is consumed. It remains available for a configured retention period. 3. Kafka is a stream processing platform. This means data can be processed in real time while it flows through Kafka without waiting for batch processing. The problem before Kafka: point-to-point integrations. Imagine the Orbit ETL system starts growing and multiple services need to communicate with each other. In a traditional architecture, the orchestrator directly calls multiple services using HTTP. Orchestrator calls extract service using HTTP orchestrator calls, transform service using HTTP orchestrator calls, load service using HTTP orchestrator calls, notification service using HTTP orchestrator calls, audit service using HTTP. This setup works fine when the system is small. Now imagine the system grows further, and the extract service also needs to communicate with multiple other services. Extract service calls orchestrator using HTTP extract service calls, monitoring service using HTTP extract service calls, audit service using HTTP extract service calls, notification service using HTTP extract service calls, analytics service using HTTP. At this point, every service starts talking to multiple other services. If there are n services in the system, the number of connections becomes n multiplied by n-1. This creates a serious architectural problem known as integration spaghetti. Problems with this approach: extract service must be aware of every service that consumes its data. Adding a new consumer requires modifying the producer service. This violates the open-closed principle because existing code must change for new behavior. If any downstream service like notification service is down, the request may fail. There is no built-in retry mechanism across all services. There is no replay capability for past events. There is no central history of what happened in the system. Every service implements its own communication logic. The entire system becomes tightly coupled and hard to scale. How Kafka solves this? Hub-and-spoke model. Kafka removes direct service-to-service communication and introduces a central event streaming layer. Instead of services calling each other, services publish events to Kafka topics. For example, the extract service publishes an event called extraction completed to Kafka. Then multiple services independently subscribe to this event. Orchestrator subscribes to extraction completed, audit service subscribes to extraction completed, monitoring service subscribes to extraction completed, analytics service subscribes to extraction completed, notification service subscribes to extraction completed. Now the extract service does not know which services are consuming its event. It simply publishes the event and continues its work. If a new service is introduced later, for example a compliance service, it can simply subscribe to the same topic without any changes required in the extract service. This removes coupling between services and creates a fully event-driven architecture. The four major problems Kafka solves. 1. Decoupling. In Kafka, producers and consumers are completely decoupled. Producers do not know who the consumers are, and consumers do not need to know who produced the data. Here is a real example of a Kafka producer in a Spring Boot application. Kafka template.send, extraction.completed, new extraction completed event, workflow ID, row count. In this case, the extract service simply sends the event to Kafka and immediately continues its execution. It does not wait for any response, and it does not know which services will consume the event. Number 2. Resilience. In traditional HTTP-based systems, if a downstream service like notification service is down, the request fails. The producer must handle retries, failures, and circuit-breaking logic. In Kafka-based systems, the event is safely stored inside Kafka topics. If a consumer service is down, Kafka does not lose the message. When the service comes back online, it continues consuming messages from where it left off. This makes the system highly resilient and fault-tolerant. Number 3. Replay capability. Kafka stores messages on disk for a configurable retention period. The default is usually 7 days, but it can be configured to be longer or even permanent. This allows consumers to replay historical events. For example, if a new analytics service is added after the system has already been running, the service can subscribe to the extraction completed topic. It can set its offset to the beginning of the topic. It can replay all events from the past 7 days. It can rebuild its entire dataset without any separate backfill job. No data migration is required. No additional ETL process is needed. This replay capability is one of the most powerful features of Kafka. Number 4. Speed and asynchronous processing. In a traditional synchronous system, execution happens sequentially. The orchestrator calls extract service and waits for the response. Then it calls transform service and waits again. Then it calls load service and waits again. The total execution time becomes the sum of all service delays. The orchestrator remains blocked during the entire process. This leads to high latency and poor scalability. In a Kafka-based system, execution becomes asynchronous. The orchestrator publishes an event called workflow triggered to Kafka extract service, transform service, and load service all listen independently. Each service processes its own event at its own pace. The orchestrator does not wait for any response. The orchestrator completes its work almost immediately. This significantly improves system throughput and responsiveness. Kafka versus traditional message queues. Kafka behaves very differently compared to traditional message brokers like RabbitMQ or ActiveMQ. In Kafka, messages are persisted on disk instead of being deleted after consumption. Multiple consumer groups can read the same message independently. Each consumer group maintains its own offset. Ordering is guaranteed within a partition. Kafka supports extremely high throughput, often millions of messages per second. Kafka is mainly used for event streaming, auditing, and replay systems. Messages are retained for a configured time period, even after being consumed. In RabbitMQ or ActiveMQ, messages are removed immediately after being consumed. Typically, only one consumer processes a message. Ordering is not guaranteed across multiple consumers. Throughput is lower compared to Kafka. It is mainly used for task queues and job distribution. There is no built-in replay capability. The key architectural difference is this: Kafka is a distributed log system, not a queue system. A queue removes messages once processed. Kafka retains messages so they can be replayed at any time, where Kafka fits in OrbitETL. Currently, OrbitETL uses HTTP-based synchronous communication between services through an API gateway. Kafka can either replace or enhance this communication model by introducing event-driven workflows. The system flow would look like this. The orchestrator publishes a workflow-triggered event. The extract service consumes the workflow-triggered event and begins extraction. The extract service publishes an extraction-completed event. The transform service consumes the extraction-completed event and starts transformation. The transform service publishes a transformation-completed event. The load service consumes the transformation-completed event and starts loading data. The load service publishes a load-completed event. The notification service and audit service consume the load completed event. If any step fails, a pipeline failed event is published. The monitoring service and notification service consume pipeline failed events and take action. This architecture brings several important benefits. Long-running ETL jobs no longer block HTTP threads in the orchestrator. If the load service becomes slow or temporarily unavailable, the transform service can continue working because Kafka buffers the events. The system gains a complete audit trail of every event that occurred in the pipeline from start to finish. New services such as analytics, compliance, or reporting can be added without modifying existing services. The system becomes more scalable and resilient under load. Tech Lead one-line explanation. Kafka solves the integration problem at scale. Instead of N services creating N-squared point-to-point connections, each service publishes events to Kafka topics and other services subscribe independently. Producers do not know their consumers. Consumers can fail and recover without losing data. Intuitive explanation of Kafka core concepts: broker, topic, partition, offset, leader, replica, and how they all fit together in one system. I'll build it step by step so the mental model becomes solid. Number 1. Broker, the Kafka server. A broker is just a Kafka server. Think of it like one machine or container that stores data and serves requests on. In a Kafka cluster, you don't have one broker, you have many brokers. So, broker 1, broker 2, broker 3. Together they form a Kafka cluster. What a broker does: stores partitions, data, serves producers, writes data, serves consumers, reads data, handles replication. So basically, broker equals storage communication node in Kafka. Number 2. Topic, the category of data. A topic is a logical name for a stream of events. Think of it like a folder or category. Example, workflow.triggered, extraction.completed, payment.success. Each topic represents one type of event stream. Important idea: a topic does not store data in one place. Instead, a topic is split across multiple partitions. Those partitions are distributed across brokers, so topic equals logical concept, data equals physically distributed. Number 3. Partition, the real storage unit. A partition is where actual data lives. A topic is divided into multiple partitions. Example, topic, extraction.completed, has 3 partitions: partition 0, partition 1, partition 2. Each partition is an ordered append-only log of events. Key properties of partitions. 1. Ordering exists inside a partition. Example, partition 0, event A, event B, event C. This order is guaranteed, but no order guarantee across partitions. Partition 1 and partition 0 may be completely independent. 2. Parallelism comes from partitions. If you have 3 partitions, 3 consumers, then Kafka can process in parallel. Each consumer reads one partition, so partition equals unit of parallel processing. Number 3. Partition decides scalability. More partitions equals more parallelism, but also more overhead. Number 4. Offset, position inside a partition. Every message inside a partition gets a number called an offset. Example, partition 0, offset 0, event A, offset 1, event B, offset 2, event C. Key properties. 1. Offset is sequential, always increases, 0, 1, 2, 3. 2. Offset is unique per partition. Offset 5 in partition 0 is different from offset 5 in partition 1. 3. Offset is a bookmark. Consumers use it to track progress. Example, open quote, I have processed up to offset 100, close quote. Now why offset matters. If a consumer crashes, it restarts from last committed offset, so no data is lost. Number 5. Leader, the main controller of a partition. Now we go deeper into Kafka cluster behavior. Each partition has a leader broker. Example, partition broker 1, partition 1, leader broker 2, partition 2, leader broker 3. What does leader do? All read and write operations go through the leader. So producer flow, producer, leader broker, writes data. Consumer flow, consumer, leader broker, reads data. Why leader exists? Kafka does not allow multiple brokers to write to the same partition at the same time. So leader equals single source of truth for a partition. Number 6. Replica. Backup copies of partitions. Kafka is fault tolerant because of replication. Each partition has replicas. Example, partition 0, leader broker 1, replica, broker 2, replica, broker 3. What replicas do? Replicas are exact copies of the partition data. They continuously sync with the leader. Why replicas exist? If broker 1 leader crashes, Kafka automatically promotes a replica, broker 2 or 3. That replica becomes the new leader. So system continues without downtime. Replica types. 1. Leader replica handles reads and writes. 2. Follower replica just copies data from leader, does not serve traffic. Nash full system picture, how everything connects. Let's combine everything. Step 1. Topic. You create a topic, extraction.completed. Step 2. Partitions. Kafka splits it. Partition 0, partition 1, partition 2. Step 3. Brokers store partitions. Broker 1, partition 0, leader. Broker 2, partition 1, leader. Broker 3, partition 2, leader. Replicas are distributed across other brokers. Step 4. Producer writes data. Producer sends event Kafka template.send extraction.completed event. Kafka routes it to a partition based on key. Step 5. Offset is assigned. Partition 0 and offset 0, event offset 1, event offset 2. Step 6. Consumers read data. Consumer group reads. Each consumer gets a partition, reads sequentially using offsets. Step 7. Failure handling. If broker fails, replica becomes leader, consumers continue reading, no data loss. Nash, one simple mental model, very important. Think of Kafka like this. Topic equals folder name, partition equals file inside folder, offset equals line number in file, broker equals machine storing files, leader equals active writer, reader of file, replica, backup copy of file. Final tech lead summary. Kafka is a distributed log system built for scale and reliability. A topic is a logical stream of events. Each topic is split into partitions, which are ordered logs of data that enable parallel processing. Every message inside a partition has an offset, which acts as a sequential position and consumer bookmark. Brokers are the Kafka servers that store partitions and serve requests. Each partition has a leader broker that handles all reads and writes, while follower replicas maintain copies for fault tolerance. If a leader fails, a replica is promoted automatically, ensuring high availability. Together, these concepts allow Kafka to provide scalable throughput, strong ordering guarantees within partitions, and fault-tolerant distributed processing.
Kafka Producer is a client that publishes messages to a Kafka topic. It decides which topic to write to, which partition within that topic, and how to handle failures. What happens when you call kafka-template.send? It is not just message goes to Kafka. There are 6 steps internally. 1. Serialize. Convert key and value to bytes. 2. Partition. Decide which partition this message goes to. 3. Accumulate. Add to in-memory batch called record accumulator 4, send batch. Background thread called sender ships batch. To broker 5. Broker acts. Broker confirms it received the message 6. Callback. Completable. Future completes with success or failure. In orbit ETL. Extract service producer. From extraction. Event publisher. .java. Code block. 3 things to notice. 1. Workflow. It is the partition key. All batches for the same workflow always land on the same partition. Order is guaranteed per workflow. 2. Async with callback. Send. Returns immediately. The when complete fires when the broker acknowledges or fails. 3. Send result gives back partition and offset. We log it so we can trace exactly where in Kafka this message landed. Producer configuration. What controls behavior? From Kafka producer config.java. Code block. How partitioning works, the producer decides partition using this logic in order. 1. Explicit partition specified in sendee, call, use it. 2. Message has a key, hash key, %num partitions. 3. No key, round robin, across partitions. In orbit ETL, workflow id.toString go is always the key. Code block. Example, workflow id 101, hash 101. 3. Partition 1. Always. Workflow id 102, hash 102, % 3, else, partition 2, always. Workflow id 103, hash 103, % 3, partition 0, always. All batches for workflow 101 always go to partition 1. The transform service consumer on partition 1 processes them in order, batch 1 before batch 2 before batch 3. This is critical for a multi-batch ETL pipeline. Batching, how the producer buffers messages. The producer does not send one message at a time. It accumulates messages in memory and sends in batches. Code block, linger.ms equals to 5. Wait up to 5 messages for more messages before sending the batch. Batch.size equal 16 KB. Send immediately. If batch reaches 16 KB, regardless of linger.ms, whichever condition hits first triggers a send. This is why send returns immediately. Messages sit in the buffer and the background sender thread ships them. Sync versus async. Send, the trade-off. Code block. Async is right for orbit ETL. Extraction produces many batches, and blocking on each one would serialize the whole pipeline. What happens when the broker is unavailable? Code block. With enable. Dempotence. Config. true. Retries will not produce duplicates even if the broker received the message, but the acknowledgement was lost in transit. Producer summary port code block tech lead one-liner for interviews. The producer's job is to get messages reliably into the right partition in the right order. The three decisions it makes are which partition via key hashing, so all messages for the same workflow, it stay ordered on the same partition, how to batch using linger.ems and batch.size to control the throughput versus latency trade-off, and how to confirm delivery where AXALL means we wait for all in-sync replicas to confirm before calling it done. In Orbit ETL, every publisher uses workflow-id as the partition key and async callbacks to log partition and offset, so we can trace exactly where in Kafka any extraction batch landed. Kafka broker and cluster. Study notes. What is a broker? A Kafka broker is simply a server that stores messages and serves them to producers and consumers. It is just a JVM process running on a machine. What a broker does: receives messages from producers, writes to disk as a commit log, serves messages to consumers, reads from disk, manages partition replicas, keeps copies in sync, handles consumer group coordination, assigns partitions to consumers. A single broker can handle hundreds of topics and thousands of partitions, but you never run just one, because one broker means one point of failure. What is a Kafka cluster? A Kafka cluster is a group of brokers working together. They share the load, replicate data between each other, and together appear as one Kafka system to producers and consumers. Kafka cluster contains broker 1 on port 9092, broker 2 on port 9093, and broker 3 on port 9094. Producers and consumers connect to any broker. The broker they connect to is called the bootstrap broker. It hands back metadata about where all partitions actually live, and the client connects to the right broker from there. How partitions are distributed across brokers. This is the key job of a cluster. Spread data so no single broker is a bottleneck. Topic: orbitetl.raw, data with 3 partitions and replication factor 3, broker 1, partition 0 as leader, partition 1 as follower, partition 2 as follower broker 2, partition 1 as leader, partition 2 as follower, partition 0 as follower. Broker 3, partition 2 as leader, partition 0 as follower, partition 1 as follower. Every partition has one leader, the broker that handles all reads and writes for that partition, and n-1 followers, brokers that replicate the leader's data. Producers always write to the leader. Consumers always read from the leader by default. Followers exist purely for fault tolerance. Leader and follower in action. Orbit ETL extract service publishes to orbitetl.raw data. Producer asks bootstrap broker, who is leader for raw data partition 1? Bootstrap broker responds, broker 2 is the leader for partition 1. Producer sends message directly to broker 2. Broker 2 writes to its local log. Broker 1 and broker 3 replicate from broker 2 through ISR sync. Broker 2 sends ACK back to producer per AX config. Consumers do the same, ask who is leader for the partition they are reading, then connect directly to that broker. What happens when a broker goes down? Broker 2 crashes. Partition 1 leader is gone. Kafka controller detects failure via missed heartbeats. New leader elected from ISR, in-sync replicas. Broker 1 or broker 3 becomes new leader for partition 1. Producers and consumers reconnect to new leader. Zero data loss because ISR was in sync before crash. This is why replication factor matters. With factor 3, you can lose 2 brokers and still serve data. Replication factor 1, data on 1 broker. Broker dies, data gone. Replication factor 2, data on 2 brokers, survive. 1, failure. Replication factor 3, data on 3 brokers, survive. 2 failures. In or by diddle, DOA comps of Kubernetes Satuil DOA comps for local development, single broker and code block. Single broker is fine for local development. No replication needed when running on one machine. In Kubernetes for production, the Helm chart deploys a proper cluster with configurable replicas, replication factor matching broker count, and partitions distributed across all brokers. Bootstrap servers, how clients find the cluster. This appears in every service configuration. Code block. The Bootstrap server is just the entry point. The client connects to it once, gets a full map of every broker and every partition leader, then connects directly to the right brokers for all future communication. Client connects to Kafka 9092 as Bootstrap, receives cluster metadata, broker 1 at host 1, 9092, broker 2 at host 2, 9093, broker 3 at host 3, 9094, raw data partition 0. Leader is broker 1 raw data partition 1 leader is broker 2 raw data partition 2 leader is broker 3 client connects directly to correct brokers. Bootstrap server no longer involved. This is why even if the Bootstrap broker goes down after startup, the client continues working. It already has the full metadata, broker responsibilities, summary storage, writes messages to disk as commit logs using sequential I/O, which is very fast. Replication, followers pull from leader and stay in sync. Leadership, one broker is controller and manages leader elections coordination, tracks consumer group membership and triggers, rebalances retention, enforces retention policy by deleting old segments after end days or size limit cluster sizing. What a tech lead thinks about dev and test. One broker, no replication. Simple and fast to spin up staging, silent 3 brokers. Replication factor 2, catches config issues. Production, 3 or more brokers. Replication factor 3, partitions equal to max consumers. You will run rules of thumb. Replication factor should never exceed broker count. Partition count should be greater than or equal to number of consumer instances. You will scale to more brokers means more parallelism, more fault tolerance, and more cost tech lead one-liner for interviews. A broker is just a Kafka server. It stores partitions on disk and serves them to producers and consumers. A cluster is multiple brokers working together so that partitions are distributed across machines, replicated for fault tolerance, and load balanced across the cluster. The key mechanism is leader election. Every partition has exactly one leader, broker, that handles all reads and writes, and followers replicate it. If a broker dies, the controller promotes a follower from the ISR to leader within seconds, and the cluster keeps running with 0 data loss. In Orbit ETL, we run a single broker locally for dev and a multi-broker cluster in Kubernetes, and all services point to the same Bootstrap server address, which hands them the full cluster topology on first connect. Kafka Consumer and Consumer Group. Study notes. What is a consumer? Kafka Consumer is a client that reads messages from a topic partition. Unlike a queue where the message disappears after being read, Kafka consumers read from the log and track their own position using offsets. How a consumer works internally. 1. Subscribe to topics. 2. Poll for messages. Consumer pulls. Kafka never pushes. 3. Process the messages. 4. Commit the offset. Tell Kafka I have processed up to here. 5. Go back to step 2. The key word is pull. The consumer decides when to ask for messages. Kafka never pushes to consumers. This is different from RabbitMQ, where the broker pushes messages to consumers. In Orbit ETL, transform service consumer from extraction. Event consumer, Java in transform service, code block. 2 things to notice. 1. Acknowledgement. Acknowledgement. Manual offset commit. We only commit after the message is successfully processed and published downstream. If transform fails, offset is not committed. Message stays available for retry. 2. Group ID. This consumer belongs to a consumer group. That is where scaling happens. The problem without consumer groups: 1 consumer, 1 topic, 3 partitions. Partition 0, batch 1, batch 2, batch 3, batch 4, partition 1, batch 1, batch 2, batch 3, batch 4, partition 2, batch 1, batch 2, batch 3, batch 4. Single, consumer reads partition 0, then partition 1, then partition 2, sequential, one at a time. Single consumer handles everything. If extraction is fast and produces 300 batches, one consumer thread processes them one by one. Bottleneck, consumer group, parallelism. A consumer group is a set of consumers that cooperate to read a topic. Kafka assigns each partition to exactly one consumer in the group at a time. Consumer group, transform service group, topic, orbitetl.raw. Data with 3 partitions. Partition, 0, transform. Instance, 1. Partition, 1, transform. Instance, 2. Partition, 2, transform. Instance, 3. 3 consumers, 3 partitions, processed in parallel. Triple the throughput. The rule, 1 partition, 1 consumer in the group, at most. 3 partitions, 3 consumers. Perfect. Each reads 1 partition, 3 partitions, 2 consumers. 1 consumer reads 2 partitions, 1 reads 3 partitions, 4 consumers. 3 busy, 1 idle with no partition to assign, 3 partitions, 1 consumer. 1 consumer reads all 3 partitions. More consumers than partitions means idle consumers. Scale partitions first if you need more parallelism. Multiple independent consumer groups. Different groups get their own independent copy of every message. Topic, orbital job status consumer, group notification service group. Notification instance 1 reads partition 0 at offset 47. Notification instance 2 reads partition 1 at offset 51. Consumer group orchestrator service group orchestrator instance 1 reads partition 0 at offset 47. Orchestrator instance 2 reads partition 1 at offset 51. Both groups receive every message independently. Notification service sends the email. Orchestrator service logs the pipeline status. Neither interferes with the other's offset. This is the fundamental difference from a queue. In RabbitMQ, one consumer gets a message. In Kafka, every consumer group gets it. In OrbitETL, 2 groups consume job status, code block. Both listen to orbitetl job status. Both get every event. Their group IDs are different. Notification service group versus orchestrator service group. So Kafka tracks their offsets separately. What happens when a consumer crashes? Rebalancing before the 3 consumers, 3 partitions. Transform instance 1. Partition 0, transform instance 2. Partition 1, transform instance 3. Partition 2, transform instance 2, crashes. Kafka detects missed heartbeat after session, timeout.ends, rebalance triggered. After 2 consumers, 3 partitions, transform instance 1, partition and partition 1, took over, transform instance 3, partition 2. Because transform instance 2 had not committed offset 51 on partition 1 when it crashed, transform instance 1 picks up from offset 51. No message lost. This is why manual acknowledge matters in OrbitETL. If we auto-committed and the consumer crashed after commit, but before processing completed, we would lose that message silently. Consumer group offset tracking. Each group's position is stored in the consumer offsets topic. Group notification service group, orbitetl.job status. Partition 0, offset 23, orbitetl.job status. Partition 1, offset 19. Group orchestrator service group, orbitetl, job status. Partition 0, offset 23, orbital, job status. Partition 1, offset 17, behind by 2. They track independently. If orchestrator service is slow or was down, it catches up at its own pace without affecting notification service. Consumer group, the complete picture in OrbitETL extract service publishes to orbitetl.raw data, which is consumed by transform service group running extraction event consumer. Transform service publishes to orbitetl.transform data, which is consumed by load service group running transformed event consumer. Lois service publishes co obishedi obshow switches contra dependent groups. Notification service group running job status consumer and orchestrator service group running job status consumer. Clean, independent, each group at its own pace. Tech lead one-liner for interviews. A consumer reads from partitions by pulling messages and committing offsets to track progress. A consumer group is how you scale reads. Kafka assigns each partition to exactly one consumer in the group, so adding consumer instances adds parallelism up to the partition count. The power of consumer groups is that different groups are completely independent. Both notification service and orchestrator service consume orbitetl.jobStatus at their own pace, each getting a full copy of every message, because Kafka tracks their offsets separately. In Orbit ETL, we use manual offset commits everywhere. Acknowledgement.acknowledge only fires after the message is processed and published downstream, so a crash never loses a batch in flight. Zookeeper and KR Raft. Study notes. What is Zookeeper? Zookeeper is a distributed coordination service, a separate system that Kafka historically used to manage, cluster metadata and coordinate brokers. Think of it as Kafka's external brain. Zookeeper stored which brokers are alive, which broker is the controller, the one making decisions, which broker is the leader for each partition, topic and partition configuration, consumer group offsets in older Kafka versions, access control lists. Kafka brokers did not talk to each other directly for coordination. They all talked to Zookeeper, and Zookeeper kept everyone in sync. Architecture with Zookeeper. Zookeeper, so cluster, has 3 nodes, ZK1, ZK2, ZK3. All Kafka brokers register with Zookeeper. When broker 2 starts, broker 2 tells Zookeeper, I am alive. I am broker 2. Zookeeper tells all brokers, broker 2 joined. When broker 2 dies, Zookeeper detects heartbeat lost. Zookeeper tells controller broker, broker 2 is gone. Controller elects new partition leaders for broker 2's partitions. The problems with Zookeeper: problem 1, operational complexity, 2 systems to run without Zookeeper, deploy Kafka, done. With Zookeeper, deploy Zookeeper cluster with 3 to 5 nodes, configure Kafka to connect to Zookeeper, monitor Zookeeper separately, upgrade Zookeeper separately, secure Zookeeper separately, then deploy Kafka. 2 systems, 2 failure domains, 2 sets of runbooks. Problem 2, metadata bottleneck. Zookeeper could not scale. All brokers write metadata to Zookeeper. All brokers read metadata from Zookeeper. Zookeeper is a single write point. Large clusters with 1,000 or more brokers and millions of partitions cause Zookeeper to become the bottleneck. Startup time was measured in minutes. Leader election during failure took 10 to 30 seconds. Problem 3. Split brain risk. Network partition splits cluster in 2 halves. Both halves cannot reach Zookeeper. Both halves stop accepting writes, safe but unavailable. Or both halves elect their own Zookeeper leader. 2 sources of truth. Data divergence. Problem 4. Scaling limit of around 200,000 partitions maximum large Kafka deployments hit Zookeeper's scaling. Netflix, LinkedIn and Confluent all ran into this wall. What is K-Raft? KR Raft, Kafka Raft, is Kafka's built-in consensus protocol that replaces Zookeeper entirely. Introduced in Kafka 2.8 in 2021, production ready from Kafka 3.3 in 2, Zookeeper fully removed in Kafka 4.0 into 4. The idea, Kafka manages its own metadata using a Raft-based log stored in Kafka itself. No external system needed. Before KR Raft, Kafka cluster plus Zookeeper cluster equals working system. After Craft, Kafka cluster alone equals working system. How Craft works: in Craft, a subset of brokers become controllers. They form a Raft quorum and manage all cluster metadata. Craft cluster with 3 brokers all having controller role. Broker 1 as controller, and broker 2 as controller, and broker 3 as controller and broker. All 3 form a Raft quorum and elect 1 active controller. Active controller, say broker 1, owns the metadata log, handles all metadata writes, replicates to other controllers via Raft follower controllers. Broker 2 and broker 3 Replicate the metadata log, ready to take over instantly if broker 1 dies. In larger clusters, dedicated controller nodes handle only coordination, and separate broker nodes handle only data storage. Raft consensus. How controllers agree Raft is a consensus algorithm. It ensures all controllers agree on the same metadata. Client request. Create topic orbitetl.raw data with 3 partitions. Active controller receives request. Writes to metadata log, the Raft log. Sends log entry to follower controllers. Majority, i.e. quorum. Acknowledge receipt. 2 of 3 is enough. Active controller commits the entry. Return success to client. Follower controllers apply the change to their state. Majority of controllers must agree before any metadata change is committed. Semi-principally as zookeeper, but built into Kafka itself with no external dependency. What changed in KR Raft? Comparison metadata stored in zookeeper mode stores in zookeeper, K-Raft mode stores in Kavos and Klazumahada Tuvu. Cordila zookeeper mode. Uses zookeeper Zudi. Ensemble. K-Raft mode uses Raft quorum of controller brokers. Systems to deploy. Zookeeper mode needs Kafka plus Zookeeper. K-Raft mode needs Kafka only. Startup time for large cluster. Zookeeper mode takes minutes. K-Raft mode takes seconds. Failover time. Zookeeper mode takes 10 to 30 seconds. K-Raft mode takes under 1 second. Maximum partitions. Zookeeper mode supports around 200,000. K-Raft mode supports millions. Kafka 4.0. Zookeeper mode removed. K-Raft mode required. In Orbit ETL, Docker Compose shows the transition. The older Zookeeper setup in Docker Compose.yml code block. 2 containers. Zookeeper dependency explicit. The KR Raft mode setup. No Zookeeper container needed, code block. 1 container instead of 2. No Zookeeper to monitor, upgrade, or secure separately. Leader election speed. Why it matters. Zookeeper mode. Broker dies. 1. Zookeeper detects missed heartbeat. 6 seconds for session. Timeout. Then S2. Notifies Kafka controller 3. Controller reads partition list from Zookeeper 4. Elects new leaders, writes back to Zookeeper 5. Notifies all brokers of new leaders, total. 10 to 30 seconds of unavailability for affected partitions. K. Raft mode. Broker dies. 1. Active controller detects missed heartbeat. Milliseconds. 2. Metadata already in memory. No Zookeeper round trip needed 3. New leader elected and committed via Raft 4. All controllers already have the metadata. Total under 1 second for Orbit ETL. A 30-second Kafka unavailability during a broker failure means 30 seconds of backed-up extraction events and pipeline stalls. Sub-second with KR Raft means the pipeline barely notices. Tech, LED, onliner, for interviews. Zookeeper was Kafka's external brain, a separate distributed system that stored all cluster metadata and coordinated broker leadership. It worked but created operational overhead. 2 systems to deploy, monitor, and secure, plus Zookeeper, became a scaling bottleneck above around 200,000 partitions and made failover take up to 30 seconds. Kraft replaces it by building consensus directly into Kafka using the Raft protocol. A subset of brokers form a quorum and manage metadata in Kafka's own log. The result is 1 system instead of 2, sub-second failover, and no hard partition sealing. Kafka 4.0 removed Zookeeper entirely, so any new deployment today should be K-Raft. And in Orbit ETL, our Docker Compose still uses Zookeeper from when we set it up, which is worth migrating. Idempotent producer and exactly once semantics. Study notes, the 3 delivery guarantees. Quick context. At most once. Message delivered 0 or 1 times. Loss possible. No duplicates. At least once. Message delivered 1 or more times. No loss. Duplicates possible. Exactly once. Message delivered exactly 1 time. No loss. No duplicates. Default Kafka with retries enabled gives you at least once. The idempotent producer and transactions get you to exactly once. The problem, why duplicates happen. Imagine this sequence of events. Producer sends batch 2 with sequence number 1 to broker 1. Broker 1 writes to disk successfully. Broker 1 sends acknowledgement back to producer. Network drops the acknowledgement. Producer never receives it. Producer times out and assumes the message was never received. Producer retrieves, sends batch 2 again. Broker 1 writes batch 2 again. Duplicate. The broker wrote it successfully the first time. The producer did not know, so it's sent again. The consumer now sees batch 2 twice. This is at least once. Duplicates are possible. Idempotent producer, solving duplicates within a session. Idempotent means sending the same message multiple teams has, the same effect as sending it once. You enable it with one configuration line, code block. Two things happen when you enable this. Thing 1, producer gets a unique producer ID called PID. When the producer starts, the broker assigns it a unique PID. This identifies this specific producer instance for its entire lifetime. Thing 2, every message gets a sequence number. Producer with PID 42 sends messages like this. Batch 1, PID 42, sequence number 0, batch 2, PID 42, sequence number 1, batch 3, PID 42, sequence number 2. The broker tracks the last committed sequence number per PID per partition. Broker state, PID 42, partition 1, last committed sequence number is 1. Now the producer retries batch 2 with sequence number 1. Broker sees sequence number 1 but last committed is already 1. Broker discards the duplicate silently. Broker sends acknowledgement to producer as if it was a fresh write. Consumer never sees batch 2 twice. Problem solved, within one session. What idempotent producer does not solve, the idempotent producer only protects one producer session, one topic, one partition. It does not protect against everything. Scenario 1. Producer restarts and gets a new PID. Original producer with PID 42 sends batch 2 and crashes before receiving acknowledgement. Producer restarts and gets PID 43. Brand new session. Retrieves batch 2 with PID 43. Sequence number 0. Broker sees PID 43. Sequence number 0. Looks completely new to the broker. Broker writes it again. Duplicate. The broker has no way to know that PID. 43 is the same logical producer as PID 42. They look like two different producers. Scenario 2. Read, process, write consumer reads job status event at offset 5. Calls external REST API to update workflow status. REST API succeeds. Consumer crashes before committing offset 5. Consumer restarts and rereads offset 5. Calls REST API again. Duplicate external call. Idempotent producer has nothing to do with this scenario. The problem is between the consumer offset and the external system. Scenario 3. Two topics need to be written atomically. Load service loads data to database successfully. Load service tries to publish to job status topic, but broker is down. Data loaded, but notification never sent. Inconsistent state. For these three scenarios, you need Kafka transactions. Kafka transactions exactly once across boundaries. Transactions let you atomically publish to multiple topics and commit offsets. All succeed or all fail together as one unit. You configure a transactional ID. This is the key difference from idempotent producer. The transactional ID survives producer restarts. Same ID means same logical producer, even after a crash and restart. Code block. Then you wrap your publishers in a transaction. Code block. The broker either commits both writes to both topics or rolls both back. The consumer never sees a partial state where one message arrived but not the other. Exactly. Once, consume transform produce. This is the most powerful pattern. Read from one topic, process, write to another topic, commit the offset, all atomically in one transaction. Code block. Steps 2 and 3, publish and commit offset, happen atomically inside the same transaction. If the broker crashes between publish and offset commit, the whole transaction rolls back. On restart, the consumer rereads the same message and processes it again. The rolled back publish never reached any consumer, no duplicate, no loss. In Orbit ETL, current state versus ideal state, current state, at least once with idempotent producer, code block, and in the consumer, code block. What could go wrong with current setup? Transform service processes batch 2 successfully. Publishes to transform data successfully. Crashes before acknowledgement acknowledge is called. Restarts and rereads batch 2 because offset was never committed. Publishes to transform data again. Duplicate batch ideal state exactly once with transactions code block. Then wrap consume and publish atomically code block. Now publish and offset commit happen atomically. Crash between them rolls everything back. No duplicate, no loss. For a production ETL pipeline exactly once matters. A duplicate batch means duplicate rows in the target database. Idempotent versus transactional. When to use which? Idempotent producer. Protects against duplicate publishes within one producer session. Scope is single producer to single partition. Minimal overhead. One configuration flag to enable. Delivery guarantee is at least once moving towards near exactly once. Orbit ETL current status. Enabled Kafka transactions. Protects against duplicates across restarts. Partial write and offset and publish misalignment. Scope is multiple topics plus offset commits atomically. Moderate overhead due to coordinator round trips. Requires transactional ID plus transaction-aware consumers. Delivery guarantee is true exactly once. Orbit ETL, current status, not yet implemented, worth adding. How to remember the difference. Idempotent producer is like a cashier who remembers your order number. If you accidentally submit the same order twice in one visit, they catch it and only charge you once. But if you leave the store and come back, they do not remember you. New visit, new order. Transactions are like a signed contract. Both the cashier and you sign. Either both signatures exist, and the deal is done, or neither signature exists and nothing happened. No partial state where one signed and the other did not. Tech lead one-liner for interviews. The idempotent producer solves the retry duplicate problem within a single producer session by assigning a producer ID and sequence number to every message. The broker detects and discards retried duplicates without the producer needing to know. But idempotency alone does not survive producer restarts or protect cross-topic atomicity. That is what Kafka transactions solve. Transactions let you atomically publish to multiple topics and commit consumer offsets in one unit, so the consume transform publish cycle is exactly once end-to-end. In Orbit ETL, we have idempotent producers enabled across all three publishing services, which gets us to near exactly once for the happy path. But adding transactional IDs and wrapping each consume-publish pair in a transaction is the right next step for a production ETL where duplicate rows in the target database are a real problem. Replication. Leader, follower, ISR. Study notes. Leader. Every partition has exactly one leader broker. All producer writes and consumer reads go through it. Orbitetal.raw data, partition 0. Leader is broker 1, orbitetal.raw data, partition 1. Leader is broker 2, orbitetal.raw data, partition 2. Leader is broker 3, follower. Every other broker that holds a copy of that partition is a follower. Followers pull from the leader continuously to stay in sync. They serve no reads or writes. They exist purely for fault tolerance. Partition 0. Broker 1 is leader. Producers write here, consumers read here. Broker 2 is follower, silently replicating. Broker 3 is follower, silently replicating ISR. In-sync replicas. ISR is the set of replicas that are caught up with the leader within a configurable time window called replica. Lag, time, max, emis, which defaults to 10 seconds. Normal state, all caught up. ISR, broker 1 as leader, broker 2, broker 3. Broker 3 falls behind due to slow network or GC pause. ISR equals broker 1, broker 2, broker 3 removed from ISR. Broker 3 catches up. ISR is broker 1, broker 2, broker 3. Broker 3 reinstated ISR is what makes AXI all meaningful. The producer waits for all ISR members to confirm, not all replicas. If a follower is lagging, it is removed from ISR so it does not block the producer. Leader failure What happens, broker 1, which is leader for partition 0 crashes, Kafka controller detects missed heartbeat, new leader elected from ISR only. Only ISR members are eligible, they have all committed messages. A lagging follower outside ISR is never elected. It would cause data loss. Broker 2 becomes new leader for partition 0. Producers and consumers reconnect to broker 2. Broker 1 comes back, rejoins as follower, catches up, and re-enters ISR. In Orbit ETL, in local Docker Compose, single broker, no replication. Replication factor is 1, no followers. In Kubernetes production, replication factor 3, min.insync.replicas out 2. Axial plus min.insync.replicas 2 means at least 2 brokers must be in ISR for a write to succeed. If ISR shrinks to 1 because 2 brokers are down, producer gets not enough replicas exception. Fail loudly rather than risk data loss. Tech-led one-liner for interviews. The leader handles all traffic for a partition, followers replicate it silently, and ISR is the set of followers current enough to be eligible for leader election. The combination of axial and a min.insync.replicas is what gives you a hard durability guarantee. A write is only confirmed when enough replicas have it that losing any single broker cannot lose the data. Kafka retention policy. Study notes. What is retention? Kafka keeps messages on disk after they are consumed. Unlike a queue that deletes on read, retention policy controls how long Kafka keeps them. 2 dimensions, time and size. Whichever limit is hit first triggers cleanup. Time-based retention deletes segments older than a configured duration. Code block. Day 1, messages written to partition. Day 8, those messages deleted because they are past the 7-day window. Day 8 onwards, new consumers cannot replay these messages. They are gone. Size-based retention. Delete oldest segments when the partition log exceeds a size limit. Code block. Partition 0 grows to 1 G. Oldest log segment deleted. Size drops back under limit. New messages continue writing. Both together, whichever triggers first, code block, high volume topic, hits 1 GB in 2 days, size limit triggers. Messages deleted after 2 days. Low volume topic takes 30 days to hit 1 GB. Time limit triggers. Messages deleted after 7 days. Log compaction. The third option, instead of deleting by time or size, keep only the latest message per key. Code block. Before compaction. Offset 0. Key workflow 101. Status draft. Offset 1. Key workflow 102. Status. Draft offset 2. Key workflow 101. Status active. Newer value. For 101 offset 3. Key workflow 101. Status inactive. Newest value for 101. After compaction. Offset 1. Key eats workflow 102. Status. Draft. Kept. Only value for 102 offset 3. Keys workflow 101. Status. Inactive. Kept. Latest value for 101 offsets. 0 and 2 are deleted because they are older values for the same key. Used for state topics where you care about current value, not history. Kafka's internal Usherman consumer offsets topic uses compaction. Only the latest offset per group and partition matters. Producer acknowledgements. AXA0, AXA1, AX all. Study notes. AXA0. Fire and forget producer sends and never waits for any response. Code block. Producer sends to broker. No acknowledgement. Moves on immediately. If broker crashes before writing, message is lost and producer never knows. Fastest. 0 durability. Use only for metrics or telemetry where loss is acceptable. Access to 1. Leader only. Producer waits for the partition leader to confirm it wrote to its local log. Followers are not consulted. Code block. Producer sends to broker 1, which is the leader. Broker 1 writes successfully. Broker 1 sends acknowledgement back to producer. but broker 2 and broker 3, which are followers, have not replicated yet. If broker 1 crashes right now, message is lost even though producer received an acknowledgement. Fast. Partial durability. Gives false confidence. You got an acknowledgement, but the message can still be lost in the replication gap. All. Full ISR confirmation. Producer waits for the leader, plus all in-sync replicas to confirm. Code block. Producer sends to broker 1, which is the leader. Broker 1 writes successfully. Broker 2 replicates successfully. Broker 3 replicates successfully. Leader sends acknowledgement back to producer only, after all ISR members agree. If broker 1 crashes now, broker 2 or broker 3 becomes the new leader, and the message is safe. Highest latency. Strongest durability. Pair with min.insync.replicas WAP2. So Kafka rejects the write rather than silently accepting it with only one replica. Code block. If ISR drops to one broker, producer gets not enough. Replicas exception. Fails loudly rather than silently accepting a write that call loss in orbit ETL code block. Correct choice. Losing an extraction batch mid-pipeline means corrupt data in the target database. The latency cost is negligible compared to the I/O cost of the extraction itself. Quick comparison. Ax at 0. Waits for nobody. Fastest speed. Yes. Data loss possible. Never used in orbit ETL. Axon 1. Waits for leader only. Fast speed. Data loss possible if leader crashes before replication. Never used in orbit ETL. Axar all. Waits for leader plus all ISR. Slowest speed. No data loss. Used by all publishers in orbit ETL. Tech lead one-liner for interviews. Ax controls the durability speed trade-off. 0 is fire and forget with possible loss. 1 confirms only the leader, which can still lose data if it crashes before replication, and all waits for every ISR member making loss impossible, as long as ma.insync.replicas is set. Orbit ETL uses Axor all everywhere. Because a lost ETL batch means corrupt output, the latency cost is worth it. Auto.offset, reset, earliest versus latest. Study notes. What it controls, auto-offset.reset, tells a consumer where to start reading when there is no committed offset for its group on a partition. 2 situations trigger this. 1. Brand new consumer group. Never read this topic before. 2. Offset expired. Committed offset is gone because retention deleted it. If the consumer already has a committed offset, this setting is ignored entirely. It picks up from where it left off. Earliest, start from the beginning. Code block. Topic. Orbitetl.job status. Partition 0 has offsets 0 through 47. New consumer group, analytics. Service group, starts for the first time. No committed offset exists. Earliest means start from offset 0 and read everything. Consumer processes offset 0, 1, 2, 3, all the way to 47. Then continues reading new messages as they arrive. Use when you care about history. New service joining needs to process all past events, replaying pipeline results, backfilling analytics. Latest, start from now. Code block. Topic. Orbitetl.job status. Partition 0 already has offset 0 through 47. New consumer group starts for the first time. No committed offset exists. Latest means start from offset 48, which is the next new message. Consumer skips offsets 0 through 47 and only reads messages arriving after it started. Use when history does not matter. A notification service starting fresh should not spam users with alerts for jobs that completed days ago. In Orbit ETL, what each service should use notification service latest. Starting fresh should not resend emails for old completed jobs. Only care about events happening from now forward. Orchestrator service latest. Pipeline coordination only needs current events. Past job completions already handled. Transform service earliest. If transform service was down and restarts, it must process all pending raw data batches that arrived while it was down. Missing a batch means incomplete data in the target database. Load service earliest. Same reasoning. Must not skip transform batches. The dangerous scenario, Offset expiry transform service was down for 10 days. Orbital.raw data retention is set to 7 days. Transform service restarts. Looks for its last committed offset, which was offset 100. Offset 100 no longer exists. Deleted by retention. Auto.offset.reset kicks in, with earliest or reads from oldest available, which might be offset 500. Some batches are permanently lost and never recoverable, but at least processes what is available. With latest, skips to newest offset. All 10 days of backlog silently dropped. Neither is good when retention has expired. This is why retention period should be longer than your maximum expected downtime for critical consumer services. For Orbit ETL data pipeline topics, set retention longer than your SLA for service recovery. Quick comparison earliest, starts at oldest available message, gets all past message. Use for pipeline services, where replay is needed, risk is reprocessing old data. Latest, starts at next new message, skips all past messages. Use for notification and monitoring services. Risk is missing backlog on restart. Tech lead one-liner for interviews. Auto.offset.reset only fires when a consumer group has no committed offset. Either it is brand new or the offset expired. Earliest reads from the oldest retained message, which is right for pipeline services like transform and load that must never skip a batch. Latest starts from the next new message, which is right for notification services, where processing old events on startup would resend stale alerts. The real danger is offset if the consumer was down longer than the topic retention period, even earliest cannot recover those messages, which is why retention on critical pipeline topics should be set longer than your worst case recovery time. Linger.ms and batch.size. Study notes. Why batching exists without batching every send. Call results in one network request to the broker, send batch, 1. Network request, broker, send batch, 2. Network request, broker, send batch, 3. Network request, broker 1000 messages equals 1000 network round trips. Network I/O is expensive. Batching groups multiple messages into one request. Send, batch port 1, goes into buffer, send, batch 2, goes into buffer, send, batch 3, goes into buffer. All three sent as one network request to broker. 1000 messages equals far fewer network round trips. Higher throughput, better compression, less broker overhead. How the producer buffer works: when you call Kafka template.send, the message does not go directly to the broker. It goes into an in-memory buffer called the record accumulator. Application thread calls Kafka template.send, and message goes into record accumulator in-memory buffer. Background sender thread picks up batches from the buffer and ships them to the broker when ready. The sender thread decides when a batch is ready to ship, controlled by linger.ms and batch.size. Batch.size does size trigger. Maximum bytes a batch can hold before it is sent immediately. Code block. Messages accumulating for partition 0. MSG1 is 2 KB. Batch is now 2 KB. MSG2 is 5 KB. Batch is now 7 KB. MSG3 is 6 KB. Batches is now 13 KB. MSG4 is 4 KB. Batchy is now 17 KB. Exceeds 16 KB limit sender ships immediately without waiting for linger.ms. Batch.size is a ceiling. Hit it and the batch goes out right away regardless of timing. Large batch.size means more messages per request, which gives better throughput but uses more memory. Linger as time trigger, how long the producer waits to accumulate more messages before sending an incomplete batch, and code block without linger.ms. Linger Marciello, which is the default. MSG1 arrives. Sender ships immediately as a batch of 1 MSG2 arrives. Sender ships immediately as a batch of 1 MSG3 arrives. Sender ships immediately as a batch of 1. Result 3 network requests for 3 messages. With linger.mn as 5. MSG1 arrives. Wait up to 5 ems. MSG2 arrives 1 ems. Later. Still waiting. MSG3 arrives 2 in May. Later. Still waiting 5 ems. Window expires. Sender ships all 3 together. Result One network request for 3 messages. Linger.ems is a waiting room. Hold messages briefly to let more arrive and batch together. Both together. Whichever triggers first. Code block. Scenario 1. High traffic. Messages arrive fast, and batch fills 16 kb in 2 megas batch dot size, triggers at 2 ES, and ships immediately. Linger.ems never reached. Scenario 2. Low traffic. Messages arrive slowly, and batch is only 3 kb after 5 ms. Linger.ms triggers and ships the 3 kb batch anyway. Batch dot size never reached. Scenario 3. Burst. 10 messages arrive simultaneously. First 16 kb batches immediately due to batch dot size. Remaining messages wait up to 5 ms due to linger.ms. In orbit ETL. Code block. For orbit ETL, workload of 5 ms linger is reasonable. Extract service publishes multiple batches per workflow run. Linger, then MST5 groups them into fewer network requests. 16 kb batch, CSA handles bursts immediately without waiting. Trade-off accepted, plus 5 ms latency per message, which is negligible for ETL, and significantly fewer broker, round trips during bulk extraction. If Orbit ETL were a real-time alerting system, Linger.msc0 would be better. Latency matters more than throughput. For batch ETL, Linger.msc 5 to 20 is fine. Tuning guide. What a tech lead thinks about optimize for throughput, bulk ETL and analytics, code block. Optimize for latency, real-time alerts and user-facing, on code block. Memory consideration, code block. If producer generates faster than sender can ship, buffer fills up, send, blocks until space is available, up to max.block.m is tech. Lead one-liner for interviews. Batching is how Kafka produces achieve throughput. Instead of one network request per message, the record accumulator buffers messages, and the sender thread ships them in groups. Batch.size triggers an immediate send when the buffer hits the size limit linger. Adds a small wait to let more messages accumulate before shipping an undersized batch. Whichever triggers first wins. For Orbit ETL, workload linger.m, ACE of 5 and batch.size, 16 kb is a reasonable default. The 5 ms latency cost is invisible against the I/O cost of database extraction, and grouping bursts of batch events into fewer broker round trips meaningfully reduces Kafka overhead. Study notes. What is compression? Instead of sending raw bytes, the producer compresses the batch before sending to the broker. The broker stores it compressed. The consumer decompresses on read. Code block. Compression is applied at the batch level. More messages in a batch means better compression ratio, because repeated patterns across messages compress well together. Why it matters: Orbit ETL extraction events carry rows of database data. Code block. Repeated field names, repeated values like Canada and active. Compression loves this. A 1 E by E extraction batch might compress to 200 kb. Benefits: network I/O. Smaller messages means less bandwidth between producer and broker. Disk storage. Broker stores compressed, which means more messages per GB. Throughput. More data per batch means fewer network round trips. The 3 algorithms snappy. Balance choice compression ratio is moderate at 2 to 4 times. Speed is very fast for both compress and decompress. CPU cost is low. Developed by Google. Prioritize is speed over ratio. Best for most Kafka use cases where throughput matters more than maximum compression. LZ4. Fastest compression ratio is moderate at 2 to 3 times. Speed is fastest of the 3. CPU cost is lowest, best when CPU is the bottleneck and you need maximum throughput. Common in high-frequency trading and real-time metrics, GZIP, highest compression ratio is high at 4 to 8 times. Speed is slowest for both compress and decompress. CPU cost is highest, best when bandwidth or storage cost is the bottleneck. For example, cross-region replication, where network is expensive, or long-term retention topics where disk matters. Not ideal for high-throughput real-time pipelines. ZSTD, modern option available from Kafka 2.1 onwards. Compression ratio is high, matching gzip at 4 to 6 times. Speed is faster than gzip, but slower than snappy. CPU cost is moderate. Best of both worlds. gzip level compression at closer to snappy speed. Worth considering for new deployments. Comparison none. Ratio 1x. Fastest speed. 0 CPU. Best for dev and test with tiny messages. Snappy. Ratio 2 to 4x. Fast speed. Low CPU. Best for general purpose and ETL. LZ4. Ratio 2 to 3x. Fastest speed. Lowest CPU. Best for ultra-high throughput. gzip. Ratio 4 to 8x. Slow speed. High CPU. Best for cross-region and archival. ZSTD. Ratio 4 to 6x, medium speed, medium CPU. Best for new deployments needing balance. Where compression is configured. And who decompresses producer compresses. Batch compressed before leaving producer. Broker stores as is. Broker does not decompress. Stores exactly what it received. Consumer decompresses. Consumer decompresses on read. Exception. If broker needs to inspect messages such as reassigning partitions or handling different topic compression settings, the broker decompresses, then recompresses, causing a CPU spike. Avoid this by keeping producer and broker compression aligned. In Orbit ETL, what to use not currently configured, so it defaults to none. For production, the recommended addition is code block, orbitetl.raw data, snappy. JSON rows with repeated field names compress well. High volume means network savings are significant. Orbitetl.transform data, snappy. Same structure as raw data. Orbitetl.jobstatus, none or snappy. Small messages with status, counts, and error strings. Compression overhead may exceed benefit for tiny payloads. Tech lead one-liner for interviews. Kafka Compression Trades CPU for network and storage. The producer compresses each batch, the broker stores it compressed, and the consumer decompresses on read, so the cost is paid at the edges, not in the middle. Snappy is the default choice for most pipelines. Moderate compression ratio with very low CPU overhead. gzip makes sense when bandwidth is expensive, like cross-region replication. LZ4 when you need absolute maximum throughput and minimal CPU. In Orbit ETL, adding snappy to the two data topics would meaningfully reduce broker storage and inter-service network traffic, since JSON extraction batches with repeated field names and values compress 3 to 4 times easily. Partitioner strategy. How a message lands on a partition. Study notes. The decision chain. Every time a producer sends a message, Kafka follows this order. 1. Explicit partition specified in send. Use it directly. 2. Message has a key. Hash the key. Partition. 3. No key. Partitioner strategy decides with a key. Consistent hashing. Code block. Kafka hashes the key and mods by partition count. Partition yield murmur. Key. %num. Partitions workflow ID'd. Under I. Murmur 2. 101. %3. Econ partition 1. Always workflow ID 102. Murmur 2. 102. %3. Ease partition 2. Always workflow ID 103. Murmur 2. 103. %3. A partition 0. Always same key, always lands on the same partition. This is what guarantees ordering for all events belonging to the same workflow. The hashing is deterministic. It does not change between producer restarts, across different producer instances, or over time. 2 separate extract service pods sending messages with workflow ID 1 will always hit the same partition. Without a key, 3 strategies. Strategy 1. Round robin. Default, before Kafka 2.4, no key. Messages distributed evenly. MSG1, partition 0. SG2, partition 1. MSG3, partition 2. MSG4, partition 0. Even distribution across all partitions. But every message is its own tiny batch, poor batching and many small network requests. Deprecated as the default. Strategy 2. Sticky partitioner. Default from Kafka 2.4 onwards. Stick to one partition until batch.size is full or linger.ms expires, MSG1. Partition 0. Same partition until batch full, MSG2. Partition 0, MSG3. Partition 0, MSG4. Partition 0. Batch shipped. MSG5. Partition 2. Picks a different partition next. MSG6. Partition 2. Better batching. Groups, messages, together before switching partitions. Same even distribution over time, but fewer and larger network requests. This is the current default. Strategy 3. Custom partitioner. Code block. Full control. Route by priority, tenant, region, or any business rule. In Orbit ETL, all three topics use keyed partitioning. Code block. Workflow ID flows as the partition key through all three topics. This means Workflow 101, raw data, partition 1 published by extract service, transformed, partition 1 published by transform service, preserving key job status, partition 1 published by load service preserving key, same consumer instance handles workflow, 101, end to end, ordering guaranteed at every stage. The partition count change problem, key-based partitioning has one trap. Today with 3 partitions, Workflow ID 101, Partition 1, add a partition, now 4 partitions. Tomorrow, Workflow ID 101, Murmur, 101, percent to 4E, Partition 3, different partition. If a consumer was mid-processing workflow, 101 events on Partition 1, and you add a partition, subsequent messages for the same workflow land on a different partition, potentially a different consumer. Ordering broken. This is why partition count should be set generously up front and never decreased. Increasing partitions midstream breaks key affinity. Hot partition problem. Bad key choices cause uneven distribution. Code block. Tenant ID. Enterprise. 80% of messages. Partition 0. Overloaded tenant ID small co. 10% of messages. Partition 1 tenant ID trial. 10% of messages. Partition 2, Partition 0 consumer is overwhelmed. Partition 1 and Partition 2 consumers are idle. Throughput limited by one partition. Fix, composite key, to distribute within tenant by workflow, id, code block, tech lead one-liner for interviews. Message routing to partitions follows a priority order. Explicit partition if specified, otherwise key hash if a key exists, otherwise the default partitioner. Key-based hashing is deterministic, murmur to key, percent partition count, so the same key always hits the same partition, which is how Orbit ETL guarantees ordering by preserving workflow, id, as the partition key across all 3 topics. The default no-key strategy is sticky partitioner since Kafka 2.4. It batches messages to one partition until full, then switches, which gives better throughput than round-robin without sacrificing even distribution. The key design decisions are choosing a partition key with good cardinality to avoid hot partitions, and setting partition count generously up front, since increasing it later breaks key affinity for in-flight messages. Consumer rebalancing and partition assignment strategies. Study notes. What is rebalancing? A rebalance is Kafka redistributing partition ownership among consumers in a group when the group membership changes. 3 triggers. 1. Consumer joins the group. New instance started, scale up 2. Consumer leaves the group. Graceful shutdown 3. Consumer dies. Missed heartbeat, session timeout. During a rebalance, all consumers in the group stop processing. This is called a stop the world rebalance. Every partition is unassigned and reassigned from scratch. How heartbeats work: consumers send heartbeats to the group coordinator broker on a background thread. Code block. Consumer alive. Background thread sends heartbeat every 3 seconds. Group coordinator sees heartbeat and considers consumer healthy. Consumer crashes due to JVM killed or out-of-memory error. Heartbeats stop. Group coordinator waits session. .timeout.ms, which is 45 seconds. No heartbeat received. Consumer declared dead. Rebalance triggered. Consumer alive but slow due to long processing. heartbeat still sent by background thread, but poll not called within max.poll.interval.ms. Group coordinator triggers rebalance anyway. Consumer processing too slow is treated like dead. Max.poll.interval.ms is the orbit ETL relevant one if transformation service. Transform takes longer than 5 minutes for a huge batch. Kafka thinks the consumer died and triggers a rebalance mid-processing. The rebalance process group has 3 consumers and 3 partitions. Consumer to 1, partition 0, consumer 2, partition 1, consumer 3, partition to 2, consumer 2, crashes. Missed heartbeat, 45 seconds pass. Group coordinator detects failure. Rebalance triggered. All consumers notified. All consumers finish current message and stop polling. Stop the world. Group coordinator collects partition assignment from all active consumers. Assignment strategy runs and redistributes partitions. Consumer 1, partition 0 and partition 1 took over consumer 2's partition, consumer 3, partition 2. Consumers resume from last committed offset on their new partitions. Consumer 1 resumes partition 1 from wherever consumer 2 last committed. If consumer 2 had uncommitted offsets, those messages are reprocessed. In orbit ETL with manual commits, this is safe. Worst case, a batch is retransformed, which is idempotent. Partition assignment strategies. The strategy determines which consumer gets which partition after a rebalance. Strategy 1. Range assigner. Default in older versions assigns contiguous ranges of partitions per topic sorted by partition number. 3 consumers, topic A with 3 partitions. Consumer 1, topic A, partition 0, consumer 2, topic A, partition 1, consumer 3, topic A, partition 2, clean pairing, but uneven when partition count does not divide evenly. 3 consumers, topic A with 4 partitions. Consumer 1, partition 0 and partition 1 gets 2. Consumer 2, partition 2 gets 1. Consumer 3, partition 3 gets 1. Consumer 1 is overloaded. The range approach always burdens the first consumer. Strategy 2. Round-robin assigner distributes partitions evenly in round-robin order across all consumers. 3 consumers, topic A with 4 partitions. Consumer 1, partition 0 and partition 3. Consumer 2, partition 1. Consumer 3, partition 2. More even. But, on rebalance, all partition assignments change. Every consumer gets different partitions, losing any warm cache or in-flight state. Strategy 3. Sticky assigner, available from Kafka, 0.11 onwards. 2 goals. 1. Distribute as evenly as possible. 2. Preserve existing assignments as much as possible during rebalance. Before rebalance with 3 consumers and 6 partitions. Consumer 1, partition 0, partition 3, consumer 2, partition 1, partition 4, consumer 3, partition 2, partition 5, consumer 2, crashes, rebalance triggered. Round robin would reassign everything from scratch, consumer chapter 1, partition 0, partition 2, partition 4, different partitions, consumer 3, partition 1, partition 3, partition 5, different partitions. Sticky assigner keeps existing assignments and just redistributes orphaned ones. Consumer upper 1, partition 0, partition 3, partition 1, kept partition 0 and 3, added partition 1 from consumer 2, consumer 3, partition 2, partition 5, partition 4, kept partition 2 and 5, added partition 4 from consumer 2, consumer 1, keeps partition 0 and partition 3, no unnecessary movement. Only the orphaned partitions, partition 1 and partition 4, are redistributed. Less disruption and less reprocessing. Strategy 4. Cooperative. Sticky assigner. Recommended from Kafka 2.4 onwards. Same sticky logic, but with incremental cooperative rebalancing, eliminates the stop the world pause. Classic rebalance with range assigner, round robin, or sticky assigner. All consumers stop, all partitions unassigned, all partitions reassigned, all consumers resume. full pause even for unaffected consumers. Cooperative rebalance with cooperative sticky assignor. Only consumers that need to give up partitions revoke them. Other consumers keep processing their partitions uninterrupted. Revoked partitions reassigned in a second round. Minimal disruption and no full stop. Consumer 2 crashes, and owned partition 1 and partition 4. Consumer 1 keeps processing partition 0 and partition 3 uninterrupted. Consumer 3 keeps processing partition 2 and partition 5 uninterrupted. Only partition 1 and partition 4 are reassigned to consumer 1 and consumer 3. No pause for unaffected consumers. In Orbit ETL, what to configure? Code block. Code block. Why cooperative sticky assignor for Orbit ETL. Transform service processes large batches, which can be slow. Stop the world rebalance means all transformation stops across all partitions. Cooperative sticky means only affected partitions pause, while other workflows keep transforming uninterrupted. Also tune session and poll timeouts for long-running ETL processing. Code block. Rebalance listener. Handle gracefully. Code block. Tech lead one-liner for interviews. Rebalancing is Kafka redistributing partitions among consumers when group membership changes. A consumer starts, stops, or crashes. Classic rebalancers like range and round robin do a stop the world pause where all consumers stop and every partition gets reassigned from scratch. Sticky assignor minimizes movement by preserving existing assignments and only redistributing orphaned partitions. Cooperative sticky assignor goes further by eliminating the full stop. Only consumers that need to give up partitions pause while others keep processing uninterrupted. For Orbit ETL, cooperative sticky assigner is the right choice because ETL batch processing is slow, and a full stop the world during a single service restart would freeze all influ transformations across all workflows. Max, poll, records and max.poll, dun interval, as the Spring Boot danger zone. Study notes how polling works under the hood. Springs at Kafka listener hides the polling loop, but underneath it runs this continuously. Code block. Poll does two things simultaneously. 1. Fetches the next batch of messages from the broker. 2. Sends a heartbeat to the group coordinator, proving consumer is alive. If poll is not called within max.poll.interval.ms, Kafka assumes the consumer is dead and triggers a rebalance, even if the heartbeat background thread is still running fine. This is the danger zone. Max.poll. Records. How many messages per poll? Code block. Controls. How many records Spring fetches from the broker in a single poll? Call partition has 2,000 messages waiting. Max.poll.records 500. Poll 1 fetches 500 records, hands to @Kafka listener one by one. Poll 2 fetches next 500. Poll 3 fetches next 500. Poll 4 fetches final 500. Your @Kafka listener method is called once per record sequentially. Spring calls poll, again only after all records from the previous poll are processed. Max, but poll.interval, the time bomb, code block. Maximum time allowed between two consecutive poll to size calls. If your @Kafka listener takes too long processing the batch from the previous poll, the next poll is delayed. And if that delay exceeds maxpoll.interval.ms, Kafka triggers a rebalance. Poll, called at t0, fetches 500 records. @Kafka listener processes record 1, takes 30 seconds due to heavy DB load. @Kafka listener processes record 2, takes 30 seconds. @Kafka listener processes record 11, now at t330 seconds. t300 seconds. Max.poll.interval.ms exceeded. Kafka says consumer has not polled in 5 minutes and must be dead. Rebalance triggered, but the consumer is alive and just busy processing. The consumer gets kicked out of the group mid-processing, partitions get reassigned, and the same messages get reprocessed by another consumer. Infinite rebalance loop if processing always takes this long. The Orbit ETL danger scenario. In transform service, a single extraction batch could be 50,000 rows. Code block, with default max.poll records, 500 and max.poll interval dentes 3 sageru, poll, fetches, 500 extraction events. Event 1 has 50,000 rows with complex rules. Takes 8 minutes to process. TC 5 minutes, max.poll, interval.ems exceeded. Kafka triggers rebalance. Consumer kicked out. Another consumer instance picks up event 1 from committed offset. Processes for 8 minutes, gets kicked out again. Infinite rebalance loop. The fix, tune both together, code block poll, fetches 10 extraction events instead of 500. Event 1 through 10 processed in around 8 minutes. 10 events at roughly 48 seconds each. TT 8 minutes, within 10-minute max, poll interval ems, poll, called again for next 10 records. No rebalance triggered. The relationship to always remember, max, poll, records x AVG, processing clock time per record must be less than max poll interval ems10, records x 48 seconds, 40 seconds, which is less than 600 seconds. Safe. 500 records x 48 seconds equals 24,000 seconds, which is much greater than 300 seconds. Rebalance loop. Session timeout versus poll interval. They are different. This is the most common confusion. Session.timeout.ms. Crash detection. How long before broker declares consumer dead after missing heartbeats? Heartbeat thread sends independently of poll. Consumer can be busy processing and still heartbeat. Max.poll.interval.ms. Processing time limit. How long between polls and calls before broker declares consumer stuck? Even if heartbeat is fine, a missed poll triggers rebalance. Consumer processing a 10-minute batch. Session.timeout.ms45s. Heartbeat thread still firing every 3 seconds. No timeout. Safe. Max.poll interval s-5m. Poll. Not called for 10 minutes. Rebalance. Dangerous. Kafka 0.1 onwards separated these deliberately. A consumer can be alive via heartbeating but stuck via not polling, and Kafka handles them differently. In Orbit ETL, recommended config per service, code block. The other approach, async processing. Instead of tuning poll interval, offload processing to a thread pool and return from the listener quickly, code block. Trade-off. Offset management becomes complex. If you acknowledge asynchronously, you can acknowledge offset 5 before offset 3 is done. Committing offset 5 means offset 3 is silently skipped on restart. For orbitetl ordered etl pipeline, synchronous processing is safer. Tech-led one-liner for interviews. Max.poll.records controls how many messages Spring fetches per poll. Call and max.poll.interval.ms is the maximum time allowed between consecutive poll calls before Kafka declares the consumer stuck and triggers a rebalance, even if heartbeats are perfectly healthy. The danger in Spring Boot ETL services is that Kafka listener processes records synchronously before poll is called again. So if 500 records, time slow, DB processing exceeds 5 minutes, you get an infinite rebalance loop where the consumer is repeatedly kicked out mid-processing. The fix is always the same equation. Max poll, records times AV processing time per record must be less than max poll interval, NEMS. In Orbit ETL transform and load services, that means dropping max poll records to 10 and raising the interval to 10 minutes to account for large batch processing time. Dead letter topic. Study notes. What is it? A dead letter topic is a separate Kafka topic where messages are sent when they repeatedly fail processing, instead of blocking the consumer, forever retrying a poison message. Normal flow, orbitetl.raw data, transform service processes, acknowledge done, failure flow without DLT, orbitetl raw data, transform service fails, no acknowledge, retries, fails, retries, forever. Partition blocked and no new messages processed. Failure flow with DLT orbitetl.raw data. Transform service fails n times. Sent to orbital.rawData DLT. Consumer moves on. Partition unblocked. DLT message investigated separately. The DLT is a safety valve. It prevents one bad message from stopping the entire pipeline. The poison message problem, extraction batch for workflow 1.1, contains corrupted rows. Transform service tries to apply rules and gets null pointer exception on row 4500. No acknowledge. Kafka retrieves from same offset. Same message, same exception forever. Meanwhile, workflow 102 batch sitting behind that offset is never processed. Workflow 103 batch is never processed. Entire partition 1 is frozen because of one bad message. Spring Kafka DLT. How to configure. Code block. Message. Fails. Attempt 1. Exception. Wait 1 second. Attempt 2. Exception. Wait 2 seconds. Attempt 3. Exception. Wait 4 seconds. Attempt 4. Exception. Sent to orbital.rawData DLT. Consumer acknowledges original message. Moves to next offset. Pipeline continues. DLT message or what it contains. Spring Kafka adds headers to the DLT message automatically. Kafka, DLT original topic, ixa edits orbital.raw data Kafka DLT original partition, one Kafka DLT original offset, isum 47 Kafka DLT original timestamp, 2026 to 06 to 10 2345 Kafka DLT exception message, null pointer exception, row 4500 has null country field Kafka DLT exception stack trace, is full stack trace Kafka DLT original consumer group, is transform service group. Full forensic, you know exactly which message failed from which partition and offset, with what error. No manual log digging needed. In Orbit ETL, DLT per topic, orbital, raw data, orbital, raw data, DLT, orbital, transformed data, orbital, transformed data, DLT, orbital, job status, orbital, job status, DLT, transform service, most likely to produce, DLT, messages, corrupted extraction data causes transformation rule crash, schema mismatch, field expected as integer arrives as string. Null values in required fields cause null pointer exception. Load service, DB constraint violations, duplicate key on target table causes data. Integrity violation exception, target table does not exist causes table not found exception. DLT consumer, process failures separately. Code block, retry versus DLT, which errors should retry. Not all errors are worth retrying. Code block, transient errors, retry with backoff, DLT after max retries, network timeout, broker unavailable, DB connection pool exhausted, permanent errors, DLT immediately, no retries, bad data format, schema mismatch, constraint violation. Current state in Orbit ETL. Currently consumers catch exceptions and log them, but no DLT is configured. Code block. Without DLT, one bad extraction batch will retry forever and block its entire partition. Adding default error handler with dead letter publishing recoverer to all 3 consumer services is a meaningful production hardening step. Tech lead one-liner for interviews. A dead letter topic is where messages go when they exhaust all retry attempts. Instead of blocking the partition forever on a poison message, the consumer sends it to a DLT topic with full diagnostic headers, including original topic, partition, offset, and exception, then moves on. Spring Kafka's default error handler with dead letter publishing, recoverer handles this automatically. You configure, retry count, back off, and which exceptions should skip retries entirely and go straight to DLT. In Orbit ETL, transform service and load service are the critical candidates. A corrupted extraction batch or a DB constraint violation would currently retry forever and freeze its partition, whereas with a DLT, it would be routed to orbital.rawData DLT after 3 attempts, the workflow marked as failed, and the user notified while the rest of the pipeline keeps running. Compaction. Study notes. What is it? Log compaction is a retention strategy where Kafka keeps only the latest message per key, instead of deleting messages by time or size. Normal retention delete policy: keep messages for 7 days, then delete everything. Log compaction: keep forever, but only the latest value per key. The result is a compacted log, a snapshot of the most recent state of every key that ever existed. How it works: before compaction, full history, offset 0, keep out workflow 101 value, what status, draft, offset 1, key cells workflow 102 value, status, draft, offset 2, key cells workflow 103 value, status, draft, offset 3, key e workflow 101 value, status, active, newer value for 101, offset 4, key e workflow 102 value, status, active, newer value for 102, offset 5, key e's workflow 101 value, status, inactive, newest value for 101, offset 6, key set workflow 103 value, status, active, newer value for 103. After compaction, offset 4, key else workflow 102 value, status, active, latest for 102, offset 5, key workflow 101 value, status, inactive, latest for 101, offset 6, key workflow 103 value, status, active, latest for 103. Older offsets for the same key are removed. The latest value for every key survives indefinitely. Tombstone. How to delete a key. To signal this key no longer exists, publish a message with the key and null value. Code block. Compacted log after tombstone. Offset. 5. Key workflow 101 value null. Tombstone. Offset 4. Key workflow 102 value on status active. Offset 6. Key workflow 3 value status active. After next compaction cycle, key workflow 101 is removed entirely. The tombstone is retained briefly for consumers to see the deletion, then cleaned up. Configure it. Code block. Compaction runs as a background thread on the broker. It does not happen instantly on every write. There is always a dirty portion of recent uncompacted messages and a clean portion of compacted messages. Clean portion contains latest value per key. Dirty portion contains all recent messages not yet compacted. New writes always go to the dirty portion. The key use case: do rebuild state from scratch. The power of compaction is that a new consumer can read the entire compacted topic and reconstruct current state without needing a database snapshot. New analytics service starts, reads orbitetl.workflow state from offset 0, sees latest value for every workflow that ever existed, builds complete in-memory state in one pass. No backfill job, no database query, just read the compacted log. This is exactly how Kafka Streams and KSQLDB materialize state. They read compacted changelog topics to rebuild their internal state stores after a restart. Kafka's internal use of compaction: Kafka uses compacted topics internally. On consumer offsets, Ching compacted. Key is group plus topic plus partition. Value is latest committed offset. Only the latest offset per consumer group per partition matters. Transaction, state, compacted. Tracks active, committed, and aborted transactions. Only latest transaction state per producer matters. In orbitetl, where compaction makes sense orbitetl.workflow state, compact, key is workflow-ed. Value is current workflow state, including status, config, and connections. New service joining needs current state of all workflows. History of intermediate states is not needed. Orbital.connection, state, compact. Key is connection ID. Value is connection config, including host, port, and credentials reference. Always want latest config. Orbital.raw data, delete, not compact. Key is workflow. It but same key has many batches. Compaction would keep only the last batch per workflow and delete all other batches. Data loss for ETL. Use time or size retention instead. Orbital.job status, delete, not compact. Audit trail. All events matter, not just latest. Compaction is wrong here. Compaction versus deletion. When to use which, use compaction when. You care about current state per key. New consumers need to reconstruct state from scratch. History of changes is irrelevant. Examples: user profiles, workflow configs, feature flags, connection configs. Use deletion when every event matters individually. You need history and audit trail. Multiple messages per key all have independent value. Examples: extraction batches, job status events, transaction logs. Tech lead one-liner for interviews. Log compaction keeps only the latest message per key instead of deleting by time or size. The result is a permanent, ever-current snapshot of the latest state for every key that ever existed. It is the right retention strategy for state topics where you care about what something is now, not its full history. In Orbit ETL, that means a workflow state topic or connection state topic where a new consumer joining can read from offset 0 and reconstruct current state without a database query. It is the wrong strategy for the data pipeline topics like raw data and transformed data, where every batch event has independent value and compaction would destroy all but the last batch per workflow. Kafka achieves high throughput. Study notes. The number first, Kafka handles millions of messages per second on commodity hardware. A single broker can sustain 100 Mbps to 600 Mbps throughput. This is not magic. It is 5 specific engineering decisions working together. 1. Sequential I/O. Write and read in order. Random disk I/O is slow. Sequential disk I/O is fast, almost as fast as memory on modern SSDs, and surprisingly fast even on spinning disks. Random I/O, like traditional databases. Write record, seek to location, write 4 KB. Write record, seek to different location, write 4 KB. Write record, seek again, write 4 KB. Disk head thrashing. Each write equals full seek time of around 10 millims on HDD. Sequential I/O, like Kafka. Write record, append to end of file. Write record, append to end of file. Write record, append to end of file. No seeking. Each write follows the last. Kafka's partition is an append-only log. Producers always write to the end. There is no insert, no update, no random seek. The OS can buffer writes in the page cache and flush to disk in large sequential batches. Benchmark on HDD. Random write, around 100 Mbps. Sequential write, around 600 Mbps. 6 times faster just by writing in order. Reads are also sequential. Consumers read from a position forward, never jumping around. The OS prefetches the next block because reads are predictable. 2. Zero copy. Skip the CPU for data transfer. Normal way to send a file over a network involves 4 copies. Disk, kernel buffer called page cache, copy 1 via DMA. Kernel buffer, application buffer, copy 2 via CPU, application buffer, socket buffer, copy 3 via CPU, socket buffer, network card, copy 4 via DMA. 2 CPU copies in the middle. CPU is involved in moving data it never needs to touch. Kafka uses Java's file channel .transfer2, which maps to the OS send file, system call, zero copy, disk, kernel buffer, called page cache, copy 1 via DMA, kernel buffer, network card, copy 2 via DMA. CPU never touches the data, 2 copies instead of 4. CPU freed for actual work like compression and coordination, code block. For a consumer reading 100 megabytes of messages, the broker never loads those bytes into JVM heap. They flow directly from disk page cache to the network socket. The broker heap stays small regardless of message volume. 3. Batching. Amortize overhead across many messages. Every network request has fixed overhead. TCP handshake, Kafka protocol headers, broker processing cost. Batching spreads that cost across many messages. Without batching, 1,000 messages times protocol overhead plus network round trip equals 1,000 times overhead. With batching, 1,000 messages in one request times protocol overhead plus network round trip equals 1 times overhead. Per message cost becomes near zero. Batching happens at 3 levels in Kafka. Producer side, record accumulator buffers messages. Linger.ems and batch.size decide when to ship. One network request carries many messages. Broker side writes entire batch to disk in one sequential operation. Stores batch compressed as received. No per message disk write. Consumer side, poll, returns up to max poll.records, messages per call. One network request fetches many messages. 4. Compression, more data per byte on the wire. Code block. Compression multiplies the effect of batching. 100 JSON extraction events, which is a typical Orbit ETL batch uncompressed. 1 MB, snappy compressed, around 250 kilobits, which is a 4:1 ratio on repetitive JSON. Same network bandwidth means 4 times more messages per second. Same disk space means 4 times more messages stored. Compression is applied to the entire batch. Cross-message patterns compress much better than single messages. Field names like workflow UD, status, and data repeated 100 times compress almost to nothing. The broker stores, the batch compresses and sends it compressed to the consumer. The broker never decompresses unless there is a compression mismatch. No CPU wasted on compress and decompress in the middle. 5 page cache does the heavy lifting. Kafka deliberately avoids managing its own memory cache. It writes to disk and lets the OS page cache handle buffering. Producer writes message, Kafka writes to file sequentially. OS keeps file in page cache, which is RAM. Disk flush happens asynchronously in background. Consumer reads message, Kafka reads from file. OS serves from page cache, which is RAM, not disk. If producer and consumer are close in offset, data never touches disk at all. Fast path when producer and consumer are near each other. Producer writes, page cache. Consumer reads from page cache. Disk never involved. RAM speed. Slow path when consumer is behind and data evicted from page cache. Consumer reads from disk. Still fast, because sequential read. This is why Kafka is JVM based, but its heap is typically small at 4 to 8 GB. The OS is doing the caching in page cache using the rest of RAM. More RAM on the broker means more data in page cache, which means more reads served from memory. All 5 together. The compounding effect, sequential I/O, fast, writes and reads with no disk seeking, 0 copy, fast network transfer with no CPU copying, batching a lower message overhead biomerizing VIX codes, compression, more messages per byte, multiplying throughput, page cache, OS serves reads from RAM when possible at memory speed. Combined result on one broker with commodity hardware, 600 ICM sites write throughput, millions of messages per second. JVM heap stays small regardless of volume. In Orbit ETL, which of these we use? Sequential or automatic, this is how Kafka works. 0 copy is automatic, this is how Kafka sends to consumers. Page cache, automatic, this is OS behavior. Batching, configured with Linger MEMSys5 and batch size send 6 KB. Compression, not yet configured. Worth adding snappy for data topics. Adding compression.type snappy to extract service and transform service producers is a low-effort improvement. Extraction batches of JSON rows with repeated structure compressed 3 to 4 times, directly reducing broker disk usage and inter-service network traffic. How to choose the number of partitions. Study notes. The core rule partitions equal maximum consumer instances you will ever want to run in parallel. More partitions than consumers, idle consumers. More consumers than partitions, idle consumers. They need to match at peak scale. The formula partitions equals target throughput divided by single partition throughput. Single partition throughput is approximately 10 Mbps write and 30 Mbps read on commodity hardware. Target 100 Mbps write throughput. 100 divided by 10 equals 10 partitions minimum. For most applications, partition count is driven by parallelism, need not throughput math. In Orbit ETL, reasoning per topic orbitetl.raw data, max transform service instances planned is 6 partitions. Orbitetl transform data, max load service instances planned is 6 partitions. Orbitetl.job status, 2 consumer groups which are notification service and orchestrator service. Each group can run 3 instances, 3 partitions. Each group independently reads all 3 partitions. Rules of thumb. Start higher than you think you need. Partitions can be increased later, but increasing breaks key affinity. Workflow D2101 was always partition 1. After adding partitions, different partition. In-flight ordering guarantees break. Better to start with 12 than 3 and regret it. Partition count has overhead. Each partition equals open file handle on broker. Each partition equals memory for leader and follower tracking. Each partition replica equals replication overhead. 1000 partitions times 3 replicas equals 3000 files open per broker. Do not create 1000 partitions just in case. More partitions equal longer rebalance. 3 partitions. Rebalance takes milliseconds. 100 partitions, rebalance takes seconds. 1000 partitions, rebalance noticeably slow. Practical guide, development and testing, 1 to 3 partitions. Small production, 3 to 6 partitions. Medium production, 6 to 12 partitions. High throughput, 12 to 50 partitions. Extreme scale, like LinkedIn and Netflix, 100 or more. Tech lead one-liner for interviews. Set partitions equal to the maximum number of consumer instances you will ever run. That is the real ceiling, since one partition serves one consumer at a time. Start generously because you can increase later, but increasing breaks. Key-based ordering guarantees for in-flight messages. For Orbit ETL, 6 partitions per data topic matches a reasonable maximum of 6 transform or load service instances, and the overhead is trivial compared to the flexibility of being able to scale horizontally when a large workflow floods the pipeline. Consumer lag and how to monitor it. Study notes. What is consumer lag? Consumer lag is the number of messages a consumer group is behind the latest offset on a partition. Orbitetl.raw data partition. 0. Latest offset, which is the producer position. Offset 500. Consumer committed offset. Offset 480. Lag, 500 minus 480 equals or 20 messages behind. Lag, 0 means consumer is keeping up with producer. Lag, growing, means consumer is falling behind. Pipeline slowing down or stalling. Why it matters in Orbit ETL extract service publishes 10,000 batches. Transform service processes 100 per minute. Lag grows at 9,900 per minute. Without monitoring, load service sees no data because transform is not caught up. Target database looks empty. No alerts fired. You discover the problem when the business asks why data is not there. Lag is the first signal that something is wrong. Slow consumer, bad message causing retries, under-provisioned instances, or GC pause. How to check lag? Command line, code block. Output, group. Transform service group topic. Orbitetl.raw data. Partition 0. Current offset 480. Log end offset 500. Lag 20 topic. Orbitetl raw data. Partition 1. Current offset 300. Log end offset 312. Lag 2 topic. Orbitetl raw data. Partition 2. Current offset 490. Log end offset 490. Lag, how to check lag. Programmatically. Code block. Monitoring in production. Key metrics. Key Prometheus metrics to watch. Kafka consumer lag sum. Total lag across all partitions. Kafka consumer records lag max. Worst single partition lag. Kafka consumer fetch rate. How fast consumer is fetching. Kafka producer record send rate. How fast producer is publishing. Alert thresholds for Orbit ETL. Code block. What causes lag and how to fix it. Slow processing. Reduce max, polars, records, and scale consumer instances. Poison message with no DLT. Add default error handler and DLT. Consumer crashed. Check logs and restart service. Not enough instances. Add more consumers up to partition count. Broker overloaded. Add brokers and rebalance partitions. Tech lead one-liner for interviews. Consumer lag is the gap between the latest offset on a partition and where the consumer group has committed. It is the single most important Kafka health metric because growing lag means the pipeline is falling behind and downstream services will see stale or missing data. Monitor it with Kafka consumergroups.sh for ad hoc checks, expose it via JMX to Prometheus for continuous monitoring, and alert on sustained lag above a threshold so you catch a slow consumer or poison message before the business notices empty tables in the target database. Back pressure in Kafka. Study notes. What is back pressure? Back pressure is what happens when a consumer processes slower than the producer publishes. Pressure builds up in the system as unprocessed messages accumulate. Extract service publishes 1,000 batches per minute. Transform service processes 100 batches per minute. After 1 minute, 900 messages piling up in orbitetl.raw data. After 10 minutes, 9,000 messages piling up. Lag growing, pipeline stalling, target database empty. Unlike HTTP, where a slow server causes the client to block or time out, Kafka never tells the producer to slow down. The producer keeps publishing regardless of whether consumers are keeping up. The lag just grows. Kafka's built-in buffer, the natural backstop. The Kafka topic itself is the buffer. This is by design. Producer at fast pace. Kafka topic as unbounded buffer. Consumer at slow pace. Producer does not block. Consumer processes at its own rate. Lag accumulates in the topic bounded only by retention. This decoupling is Kafka's core value proposition. But unbounded lag is still a problem for an ETL pipeline, where you need data to arrive in the target database within a reasonable time. How back pressure manifests in Orbit ETL 50 large workflows triggered simultaneously. Extract service publishes 50,000 batches in 10 minutes. Transform service has 2 instances and 6 partitions. Processes 200 batches per minute. Time to clear. 50,000 divided by 200 illusters 250 minutes. Over 4 hours behind. Meanwhile, load service has no transform data arriving and sits idle. Target database has no new data. Users see stale data. Handling back pressure. The options, option 1. Scale consumers horizontally. Primary solution. Lag growing on orbitetl.raw data. Spin up more transform service instances up to partition count. 6 partitions means maximum 6 parallel consumers. Throughput scales linearly. In Kubernetes, use KEDA, Kubernetes Event-Driven Autoscaler, which watches consumer lag directly and scales pods automatically. Code block. Option 2. Slow down the producer. Rate limiting. Code block. Slows the producer when downstream is overwhelmed. Trade-off. Extraction takes longer. Option 3. Producer buffer. Block instead of drop. Code block. If record accumulator fills up because broker is slow or down, producer blocks for up to 60 seconds. If still full after 60 seconds, throws timeout exception. Never silently drops messages. Option 4. Reduce batch size. Process smaller chunks. Code block. Process 5 at a time instead of 500. Each poll a cycle is shorter. Poll is called more frequently. Lag consumed more steadily. Back pressure versus lag. The distinction lag ills the symptom, how far behind the consumer is. Back pressure ill the cause. Consumer cannot keep up with producer. You monitor lag. You solve back pressure by scaling consumers, rate limiting producers, or optimizing consumer processing time. Tech lead one-liner for interviews. Back pressure in Kafka is when consumers cannot keep up with producer throughput. Unlike HTTP, there is no feedback signal to slow the producer down, so messages just accumulate as growing consumer lag. Kafka's design treats the topic as an intentional buffer for exactly this reason, but unbounded lag is still a problem for an ETL pipeline with freshness requirements. The primary solution is horizontal scaling of consumers with Kida watching lag metrics and spinning up pods automatically up to the partition count ceiling. And the secondary solution is producer-side rate limiting, when you know downstream services have a hard throughput ceiling that more instances cannot fix. How Kafka Listener works internally. Study notes. What it looks like versus what actually happens. Code block. Looks simple. Behind this annotation, Spring Kafka spins up an entire infrastructure. Here is what a tech lead needs to know. What Spring creates at startup, when Spring Boot starts, it scans for Kafka listener annotations and creates this infrastructure automatically on code block. You write one annotation. Spring creates the consumer, the thread, the poll loop, the deserializer, and the error handler. The poll loop, what runs on that thread? Code block. 3 things to understand here. 1. Same thread polls and processes. The thread that calls poll is the same thread that calls your method. If your method takes 10 minutes, poll is not called for 10 minutes. Max.poll interval.ms violated. Rebalance triggered. This is exactly what we covered in the danger zone notes. 2. Your method is called via reflection. Spring resolves at payload, at header, and acknowledgement parameters automatically through messaging, message listener adapter. You never deal with raw bytes or consumer record directly. 3. Deserialization happens before your method is called. Raw bytes from Kafka, JSON deserializer, extracted data, event object. If deserialization fails with malformed JSON, default error handler catches it and routes straight to DLT without calling your method at all. What act.acknowledge actually does, code block. 2 things to notice. It commits offset plus 1, not the current offset. Kafka convention, you commit where to resume from next time, not where you are now. It is commit async, not commit sync. Non-blocking. Does not wait for broker confirmation. Returns immediately. Increasing parallelism within one pod. Default concurrency is 1 Kafka consumer thread per pod. You can increase it, code block. This creates 3 Kafka consumer instances in one pod. Each owns different partitions. However, the recommended approach for Orbit ETL is multiple pods, not multiple threads per pod. Reason: easier to reason about, easier to scale with Kubernetes, HPA. Failure of one pod does not affect others. Error handling flow, code block. The default error handler wraps your entire method invocation. Your method only needs to handle the happy path. Error handling, retry, and DLT routing happen transparently outside your code. The full picture in Orbit ETL1 at Kafka listener annotation in transform service creates 1 concurrent message listener container, 1 background thread with default concurrency of 1 Kafka consumer joining transform service group, partition assignment via cooperative sticky assigner, poll loop running continuously on that thread, JSON deserialization via JSON deserializer, method called via reflection with @payload and acknowledgement resolved, manual immediate ACK-E mode, commits when you call acknowledgement acknowledge, default error handler wrapping the whole invocation with retry and DLT, tech lead one-liner for interviews. @Kafka Listener is a declarative wrapper over a full container infrastructure. At startup, Spring creates a concurrent message. Listener container, which spawns 1 thread per concurrency unit, and each thread runs a Kafka consumer poll loop that fetches records, deserializes bytes to your DTO, resolves method parameters, and calls your method via reflection. The critical thing to understand is that the poll loop thread and your processing thread are the same. Slow processing delays the next poll, and triggers maxpoll and interval.ms violations. The default error handler wraps the entire invocation transparently, so your method only handles the happy path while retries and DLT routing happen automatically. Kafka Listener contains R factory and concurrency. Study notes. What is it? It is the Spring Bean that creates and configures the infrastructure behind every Kafka listener in your application. Think of it as the factory that builds the engine behind each listener. You configure it once, ACK mode, error handler, deserializer, concurrency, and it applies to all at that Kafka listener methods automatically. The config in Orbit ETL, code block. What concurrency does concurrency Site 3 creates 3 independent Kafka consumer threads inside one pod. Each thread owns its own partitions and runs its own poll loop. Code block. 3 partitions processed in parallel inside one JVM. Concurrency versus multiple pods. This is the key decision for Orbit ETL. Concurrency shot 3 in one pod. Pod crashes, all 3 consumers lost. Full rebalance. Concurrency 1 in 3 pods. 1 pod crashes, only 1 consumer lost. Other 2 keep running. Small rebalance. For Orbit ETL in Kubernetes, prefer more pods over higher concurrency. Kubernetes manages pod health checks and scaling. 1 consumer thread per pod is simpler and more fault tolerant. The hard ceiling. Partition count total consumers across all pods must never exceed partition count. Total consumers equals concurrency x number of pods. 6 partitions, concurrency 2, 3 pods, total equal 6, perfect. 6 partitions, concurrency 3, 3 pods, total equals 9. 3 consumers sit idle. Idle consumers waste resources. They join the group, trigger rebalance, get no partition, and poll forever, doing nothing. Concurrency guide for Orbit ETL transform service. 3 pods, 6 partitions, concurrency 2, total 6. Perfect. Load service, 3 pods, 6 partitions, concurrency 2, total 6. Perfect. Notification service and 2 pods, 3 partitions, concurrency 1, total 2. Fine. Orchestrator service, 2 pods, 3 partitions, concurrency 1, total or 2. Fine. Tech lead one-liner for interviews. Concurrent Kafka Listener Container Error Factory is the central configuration bean for all Kafka Listener methods. It sets ACK mode, error handler, and concurrency, which controls how many Kafka consumer threads run per pod. The rule is total consumers across all pods times concurrency must never exceed partition count, or you get idle consumers. For Orbit ETL in Kubernetes, the cleaner approach is low concurrency per pod and let Kubernetes scale pod count. A single pod crash only loses its small share of partitions rather than everything. Deserialization errors in Spring Kafka. Study notes why they are special. A normal processing error happens inside your app from at Kafka listener method. Spring catches it, retrieves, sends to DLT. A deserialization error happens before your method is ever called. The bytes from Kafka cannot be converted to your DTO. Without special handling. Code block. Infinite crash loop. Partition frozen. Fix. Error. Handling deserializer. Wrap your deserializer in error handling deserializer. Instead of crashing, it catches the exception and passes a null value to your error handler with the exception stored in a header. Code block. Now the poll loop does not crash. The failed record reaches your error handler with the exception attached as a header. Wire with default error handler. Send straight to DLT. Code block. Bad JSON arrives. Error handling. Deserializer catches it. Wraps exception in header. Passes null value. Default error handler sees deserialization exception. Non-retriable. Skip retries. Send directly to orbitetl.raw data. DLT. Consumer acknowledges original, moves to next offset. No crash loop, in Orbit ETL. What the DLT consumer sees, code block, at payload required false, because the value may be null if deserialization completely failed. The original raw bytes are still available via at header, Kafka headers, DLT, original raw for forensics, tech lead one-liner for interviews. Deserialization errors are more dangerous than processing errors because they happen before your listener method is called, causing an infinite crash loop without special handling. The fix is wrapping JSON deserializer in error handling deserializer, which catches the exception and passes a null value with the error in a header instead of crashing the container, then marking deserialization exception as non-retriable in default error handler, so the bad message goes straight to the DLT without burning through retry attempts on data that will never pass correctly. Event-driven architecture versus request-response. Study notes. Request-response. How most people start: one service asks another for something and waits for the answer. Code block, synchronous, direct, easy to reason about. The caller blocks until the response arrives. Event-driven, what OrbitETL uses for the pipeline. One service announces something happened and moves on. Other services react independently. Code block, no service waits for another. Each reacts to events at its own pace. The core difference: coupling request-response. Tight coupling. Caller knows who it is calling, what it expects back, and when it will get the answer. Extract service is down. Orchestrator call fails immediately. Adding a new consumer. Must change orchestrator to call it. Extract service API changes. Orchestrator must update. Event-driven. Loose coupling. Publisher knows what happened and which topic to publish to. Publisher does not know who is consuming, how many consumers exist, or when they will process it. Extract service is down. Events queue up in Kafka, processed on recovery. Adding analytics service, just subscribe to the topic. Zero changes to publisher. Transform service slow. Load service unaffected, just waits for its own topic. When to use request response: you need the result immediately to continue. Login needs JWT token. Create workflow needs the ID back. Simple query: read data and return it. Get/workflows. Get/jobs. ID. User is waiting. Any UI interaction where user sees a spinner. Strong consistency required. Payment processing must confirm before showing success. In OrbitETL, everything through API gateway is request response. Front end, API gateway, workflow service for CRUD operations. Front end, API gateway, orchestrator service to trigger a job. When to use event-driven processing takes a long time. ETL pipeline takes minutes. Blocking HTTP for minutes is wrong. Multiple services need to react to the same thing. Job completes. Notification service, an orchestrator service, and analytics all need to know. Adding a new reactor means just adding a new consumer by some zero changes to publisher. Services should be independent. Transform service can be down for 10 minutes. Events queue up. Does not break extract service. Guaranteed delivery needed. HTTP call fails. Means lost. Kafka event means retained, retried, DLT on failure. High throughput. Extract service publishes 10,000 batches per minute. Transform service processes 1,000 per minute. 10 minutes to catch up, that is fine, pipeline still works. The hybrid reality: OrbitETL uses both request response layer through API gateway, post/API v1 jobs/trigger. Synchronous returns job execution immediately. Get API v1 jobs/ID status. Synchronous returns current status. Post API v1 workflows. Synchronous returns created workflow. Event-driven layer through Kafka pipeline. Orbitetl.raw data. Async extract to transform. Orbitetl transformed data. Async transform to load. Orbitetl job status. Async load to notify and orchestrate. The user triggers a job via REST and gets immediate job execution ID. The actual pipeline runs asynchronously via Kafka. The user polls job status via REST to check progress. Both patterns serving different needs in the same system. The decision framework: does the caller need the result to continue? Request response: is a human waiting for the response? Request response: is the operation fast under 1 second? Request response: does processing take a long time? Event-driven: do multiple services care about this event? Event-driven: should the caller be isolated from failures? Event-driven: Do producer and consumer need to scale independently? Event-driven. Is guaranteed delivery critical? Event-driven. Failure mode. The trade-offs, request response failures, easy to see, hard to handle, target service down, immediate error to caller, cascade failures, caller all fail, easy to see as 503 error in logs, hard to handle, every caller needs circuit breaker and retry logic. Event-driven failures, hard to see, easy to handle, consumer down, events queue up silently, bad message, DLT pipeline moves on, no cascade failures, publisher unaffected by consumer failure, hard to see, no immediate error, just growing consumer lag, need consumer lag monitoring to detect problems, tech-led one-liner for interviews, request response is right when the caller needs the result immediately to continue, user-facing operations, simple queries, anything where a human is waiting. Event-driven is right when processing is long-running, multiple services react to the same thing, or services need to scale and fail independently. The key insight is that event-driven trades immediate feedback for resilience and decoupling. The publisher never knows if a consumer is slow or down, which means you need consumer lag monitoring to detect problems that would be immediately obvious as a 503 in request response. Orbit ETL uses both. The API layer is request response because the front end needs immediate confirmation, and the pipeline is event-driven because ETL jobs run 4 minutes, involve multiple services, and must survive individual service failures without losing data. Streams. Study notes. Start with the problem. Why does Kafka Streams exist? You already know at that Kafka listener. It reads one message, processes it, publishes result, acknowledges. Simple. But what if you need to answer questions like, how many jobs failed for workflow 101 in the last 1 hour? What is the total rows processed across all workflows today? Alert me if any workflow fails more than 3 times in 30 minutes. These questions require memory across multiple messages. You cannot answer them by looking at one message at a time. With that Kafka listener, you would have to manually store counts in a database, manually query that database, manually handle failures and restarts, manually manage time windows. Kafka Streams gives you all of this built in. What is Kafka Streams? Kafka Streams is a Java library, not a separate server, not a separate cluster, just a dependency you add to your Spring Boot application. Code block. It runs inside your application. It reads from Kafka topics, processes events with built-in stateful operations, and writes results back to Kafka topics. At Kafka Listener versus Kafka Streams, the core difference at Kafka Listener, stateless processing. Each message is independent. You process it and forget it. No memory of previous messages. Code block. Good for Orbit ETL pipeline. Transform this batch, publish transformed batch, done. Kafka Streams. Stateful processing. Messages are related to each other. You need to remember previous messages to answer questions about the current one. Code block. Good for analytics. Count failures, aggregate totals, detect patterns over time. The topology concept Kafka Streams thinks in terms of a processing pipeline called a topology. Data flows through a series of operations like an assembly line, code block. You define the topology. Kafka Streams executes it continuously as events arrive. 2 main types of operations. Type 1, stateless operations. No memory needed filter. Keep only certain messages. Code block. Think of filter like a security gate. Every message arrives. Some pass through, some are rejected. The gate has no memory of previous messages. Map values. Transform the message and code block. Same as map in Java Streams. Converts one type to another. No memory needed. 2. Write to output topic. Code block. Publishes the result to a Kafka topic. Type 2. Stateful operations. Require memory across messages count. How many times something happened. Code block. This counts how many failed events arrived per workflow. It needs to remember previous messages. That is, the state. Workflow 101 fails, a count becomes 1. Workflow 101 fails again. Count becomes 2. Workflow 101 fails again. Count becomes 3. Without memory, you cannot count. Kafka Streams maintains this memory for you automatically. Aggregate. Combine values across messages. Code block. Every time Workflow 101 succeeds, add its rows to the running total. Job 1 loads 50,000 rows. Total equals 50,000. Job 2 loads 30,000 rows. Total equals 80,000. Job 3 loads 20,000 rows. Total equals 100,000. Running total maintained automatically across all messages. K-stream versus K-table. Very important distinction. This is the most important concept in Kafka Streams. K-stream. Every event matters independently. Think of it like a river. Water keeps flowing. Every drop is a separate event. Nothing gets overwritten a code block. All three events exist. All three matter. You use K-stream when you care about every individual event. K-table. Only the latest value per key matters. Think of it like a whiteboard. When you write a new value for a key, it erases the old one. Only the current value matters. Code block. Now only success exists for Workflow 101. You use K-table when you care about current state, not history. Simple analogy. K-stream. USLs, your phone call history. Every call is recorded. Old calls are not erased. K-table. Your phone contacts. When you update a contact number, old number is gone. Only latest number matters. Windowed operations. Time-based memory. What if you want to count failures but only within the last 1 hour? Not all time, just a sliding window. Code block. The window slides forward in time. Events older than 1 hour drop out of the window automatically. Kafka Streams manages this for you. Imagine you are counting people who walk through a door in the last 60 minutes. As time passes, people who entered more than 60 minutes ago are no longer counted. New people entering are added to the count. State stores, how Kafka Streams remembers things. All this state, counts, totals, aggregates, has to be stored somewhere. Kafka Streams uses RocksDB, a fast embedded key value database that runs on local disk inside your application. Code block. The problem? What happens if the pod crashes? RocksDB is on local disk. Pod crashes and restarts on a different node. Local disk is gone. State is lost. The solution? Changelog topic. Kafka Streams continuously backs up RocksDB state to a Kafka changelog topic. This topic is compacted. It keeps only the latest value per key, exactly like a K-table. When pod restarts, 1. Read the changelog topic from Kafka. 2. Rebuild RocksDB from the changelog. 3. Resume processing from last committed offset. 4. State fully restored. No data loss. This is brilliant because Kafka itself becomes the durable state store. RocksDB is just a fast local cache on top of it. Stream join such, combining two streams code block every time a raw data event arrives. Kafka Streams looks up the current workflow config from the K-table and joins them together. The result is an enriched event with both the data and the config information. This is like a database join, but happening in real time as events flow through, without touching a database. In Orbit ETL, where Kafka Streams fits ETL pipeline, use @Kafka Listener. Correct choice. Extract. Transform load. Each batch is independent. No state needed across batches. @Kafka Listener is simpler, easier to reason about, easier to debug. Monitoring and analytics. Use Kafka Streams. Right choice. Code block. These require state across messages. Exactly what Kafka Streams is built for. @Kafka Listener versus Kafka Streams. When to use which stateless processing. Transform this message. Publish result. @Kafka Listener. Simple, flexible, familiar. Stateful operations like count and aggregate. Kafka Streams. Built-in, no manual state management. Windowed time operations like failures per hour. Kafka Streams. Built-in time windows. Stream joins. Kafka Streams. Built-in join operations. External calls like REST API or database. @Kafka Listener. Natural fit. Orbit ETL pipeline. @Kafka Listener. Right choice. Orbit ETL monitoring and analytics. Kafka Streams. Right choice. Tech lead one-liner for interviews. Kafka Streams is a Java library for stateful stream processing. It adds the operations that Kafka Listener cannot do cleanly: aggregations, windowed counts, stream joins, and pattern detection across events over time. The key abstractions are K-stream, where every event matters independently, and K-table, where only the latest value per key matters like a materialized view, and state is maintained in local RocksDB backed by Kafka changelog topics so it survives restarts. In Orbit ETL, the ETL pipeline itself correctly uses @Kafka Listener since each batch event is stateless, but Kafka streams would be the right addition for monitoring and analytics, like counting failures per workflow per hour, computing real-time pipeline throughput, or joining job events with workflow config for enrichment, all of which require state across messages and become very complex to implement correctly with a plain consumer. Box pattern. Solving the dual write problem. Study notes. Start with the problem. What is dual write? Dual write means writing to two separate systems in the same operation. In Orbit ETL, load service does exactly this. Code block. These are two completely separate systems. There is no shared transaction between a database and Kafka, so two things can go wrong. Scenario A, DB write succeeds, Kafka publish crashes, target database has the data, but notification service never notified. Orchestrator never updates job status. User sees job stuck as running forever. Data is there, but nobody knows. Scenario B, Kafka publishes, DB write then fails. Notification service sends success email to user, but target database has no data. User gets success email, data never arrived, complete lie. Why you cannot just use a transaction. You might think, wrap both in @transactional and problem solved. No, a transactional only works within one system. A Spring transaction can wrap multiple database operations, but it cannot span a database and Kafka. They are completely separate systems with no shared transaction coordinator. Chain Kafka Transaction Manager helps in some cases. We covered this earlier, but it does not work with all database drivers and can still fail in edge cases. The outbox pattern is the robust solution. The outbox pattern, the core idea, instead of writing to DB and publishing to Kafka separately, write to the DB only, but write two things to the DB in one transaction. 1. Your actual business data. 2. A record of what you want to publish to Kafka. This is the outbox row. Then a separate process reads the outbox table and publishes to Kafka. Code block. The key insight. The outbox row is the guarantee. If it is in the database, it will eventually be published to Kafka. No matter what crashes, the outbox row survives. Step 1. Create the outbox table. Code block. Step 2. Write business data and outbox row in one transaction. Code block. Both writes are inside one @transactional database transaction. If batch update fails, the whole transaction rolls back. Outbox row never written. No false Kafka event. If service crashes after both commits, outbox row exists with published, false. Relay will publish it on recovery. Step 3. Outbox relay publishes to Kafka. A separate scheduled process reads unpublished outbox rows and publishes them to Kafka code block every 1 second, and find all outbox rows with published false, publish to Kafka. Mark as published true. If publish files delav published false, try again next second, guaranteed eventually published. What the outbox pattern guarantees DB write succeeds, Kafka publish fails during relay. Outbox row still in DB with published false. Relay retrieves next second, eventually published. DB write fails. Transaction rolled back. Outbox row never written. No false Kafka event ever sent. Service crashes after dub coming before a relay rows outbox row issues with published false. Service restarts. Relay picks it up. Published. Relay publishes but crashes before marking publisher true. Published false. Relay tries again. Duplicate Kafka message. Handled by idempotent consumer on the other end. The one remaining risk are duplicates. The outbox pattern guarantees at least once delivery. Every message will be published, but may be published more than once in crash scenarios. This is acceptable because idempotent producers prevent broker-level duplicates. Load service uses on conflict, do nothing for upserts. Exactly once can be achieved by combining outbox with idempotent consumers. Debezium Production upgrade for the relay. The scheduled polling approach works but has up to 1 second delay and adds database load from constant polling. The production approach is change data capture, CDC, using Debezium, code block. Well means write ahead log. PostgreSQL records every change to the database in this log before applying it. Debezium tails this log and reacts to changes instantly. Benefits over scheduled polling. Milliseconds latency instead of up to 1 second. No polling load on database. No scheduled job to manage. Detects changes the moment they happen. Outbox versus Kafka transactions. When to use which Kafka transactions, use when. Both systems are Kafka aware. Low latency is required. Simpler setup is preferred. Outbox pattern. Use when. Database and Kafka are completely separate systems. Database does not support distributed transactions. You need bulletproof, guaranteed delivery. You can tolerate millisecond delay, or use Debezium for near instant. For OrbitETL load service, Outbox is more robust than Chained Kafka Transaction Manager. Works with any JDBC driver. Survives any failure mode. Debezium makes it near real time. In OrbitETL, where Outbox is needed load service, critical, writes rows to target database and publishes job status to Kafka. Classic dual write problem. Extract service, not needed today. Reads from source database but does not write to its own database. No dual write problem. Transform service, not needed today. Stateless processing, no database writes. Schema evolution, Avro and schema registry. Study notes. Start with the problem. What is schema evolution? In OrbitETL, extract service publishes extracted data event to Kafka. Transform service consumes it. Today the event looks like this. Code block. 6 months later, you add a new field by code block. The problem, extract service is updated and deployed. It now publishes events with chunk size. But transform service has not been updated yet. It tries to deserialize the new message with the old schema. What happens? With JSON, it depends on your deserializer. May work, may fail, may silently ignore the field. With a strongly typed schema, it fails with a deserialization error. Consumer crashes, DLT gets flooded. This is schema evolution, managing changes to message structure over time without breaking producers or consumers. What is Avro? Avro is a binary C serialization format created by Apache. Instead of JSON, which is text, and includes field names in every message, Avro stores data in a compact binary format using a schema to describe the structure. JSON message. Field names repeated in every message about a code block. Avro message to binary field names stored in schema. Code block. Benefits of Avro. Smaller messages. 5 to 10 times smaller than JSON for repetitive data like OrbitETL batches. Faster serialization and deserialization. Schema is enforced and bad data cannot be published. Built-in support for schema evolution rules. What is schema registry? Schema registry is a separate service, not part of Kafka itself, that stores and manages schemas. Without schema registry, every service needs a copy of every schema. When a schema changes, you update it in every service manually. No validation that changes are compatible. With schema registry, code block. Every message in Kafka carries a tiny schema ID, typically 4 bytes. Consumer fetches the schema once and caches it. No full schema in every message. Avro schema definition. You define your schema in a .avsc file, code block. This is the contract. Any message published must match this schema. Any consumer reading it knows exactly what fields to expect. Schema evolution rules got it compatible versus incompatible changes. Schema registry enforces compatibility rules. It rejects incompatible schema changes before they reach production. Backward compatible. New schema can read old messages. Old message was written with schema v1. New consumer with schema v2 can still read it. Adding a new field with a default value is backward compatible. Code block. Old messages did not have chunk size. New consumer reads old message and uses the default value. 1/10,000. Works perfectly. Forward compatible. Old schema can read new messages. Old consumer with schema v1 can read messages written with schema v2, adding a new field that old consumers can ignore. Old consumer sees unknown field and ignores it. Works. Full compatible. Both directions work. New schema can read old messages and old schema can read new messages. Safest option. Requires new fields to have defaults. Breaking incompatible changes rejected by schema registry. Removing a field that has no default. Old messages have that field. New schema does not know what to do. Wish it changing a field. Keep field was it no it is shrink binary interpretation breaks completely. Renaming a field. Old messages have old name. New schema expects new name. Field not found. What schema registry does when you try an incompatible change. Code block. This protection happens before any message reaches Kafka. No consumer is ever broken by an incompatible schema change. In Orbitetl, how it works end-to-end, Producer side, extract service, code block. When extract service starts and publishes, first message, Avro serializer registers extracted data event schema with schema registry. Schema registry assigns schema ID, say ID 5. Every message published includes ID 5 in the first 5 bytes. Rest of message is compact binary Avro. Consumer side, transform service, code block. When transform service reads a message, reads schema ID 5 from first sheet bekis features shear for schema registries teki a fear first fetch deserializes binary bytes into extracted data event object. The evolution scenario with schema registry today, schema v1, code block, does not exist yet. Schema ID 1, 6 months later, add chunk size field or sub code block, added with default value. Schema ID 2, extract service updated and deployed. Registers schema v2, gets ID 2, publishes messages with ID 2, transform service not yet updated. Still on schema v1, transform service reads message with ID 2, fetches schema v2 from registry, sees chunk size field. But transform service schema v1 does not have it, uses default value 1000, continues processing normally, no crash, no DLT, no downtime, seamless evolution. Orbit ETL without Avro, current state and the gap, currently Orbit ETL uses JSON with JSON deserializer. This is fine for a single team, but has risks. No schema enforcement. Extract service can publish any JSON. If field name has a typo, transform service silently gets null. Data corruption with no error. No compatibility checking. Developer removes a field. Pushes to production. Transform service starts getting null pointer exception on every message. DLT floods. You find out from users, not from a deployment check. No size efficiency. JSON field names repeated in every message. For 10,000 row extraction batches, this is significant overhead. Adding Avro and schema registry to Orbit ETL would be a production hardening step, especially important as more teams or clients use the platform. Current JSON versus Avro comparison